Kickstart your software development career. Coursera and Amazon have partnered to bring you the Junior Software Development Professional Certificate, uniquely mapped to the key job skills required for junior software developer roles. This program offers a hands-on learning experience designed to prepare you for a rewarding career in this rapidly expanding field.
Each course in this certificate is designed and developed by subject experts to lay a solid foundation for future learning in this dynamic field. Throughout the professional certificate, you gain practical skills and hands-on experience through labs, activities, and quizzes. These opportunities will not only deepen your understanding, but also allow you to apply your knowledge in real-world scenarios.
Finally, you'll have the chance to showcase your creativity and problem-solving abilities through a course project, demonstrating your readiness to tackle challenges in software development. In this software development program, you'll work on exciting, real-world problems that bring Java programming concepts to life. One of the projects you'll tackle is building a virtual zoo management system. This project is designed to test your coding skills while introducing you to essential software development concepts. Here's a brief overview of what you'll learn.
You'll begin by understanding the core responsibilities of a developer and setting up your own Java development environment. You'll learn Java syntax and structure to write and run your initial simple programs. For example, you might create a basic calculator that can perform arithmetic operations.
You'll also explore variables, which are containers for data, and data types, like numbers or text. And you'll learn about operators, symbols for calculations. This foundational knowledge will enable you to manipulate data effectively in your programs. For instance, you could write a program to manage a list of zoo animals and their characteristics.
Then you will uncover control flow mechanisms like conditional statements for making decisions based on conditions and loops for repeating tasks. This will help you write code to manage different scenarios. For example, you might write code to handle different animal feeding schedules based on the time of day.
What's more, you'll explore advanced techniques to keep your code tidy and easy to manage. Learning object-oriented programming, or OOP, principles will help you create flexible and reusable code. For example, you might create a general animal class that includes common attributes like name, species, and habitat. You'll also develop skills in understanding the entire software development lifecycle and various methodologies used in the industry. Imagine you're organizing a big concert with your friends. You'll learn how to plan each step, from booking the venue to managing the guest list, similar to how you would manage each phase of a software project. This way, you'll know how to keep everything on track and ensure the concert or your software project is a success. Moreover, you'll gain proficiency in Git, enabling you to manage version control, track changes, and collaborate effectively on projects. For instance, you'll learn how to use Git to keep track of different versions of your code and work on team projects without conflicts. Later on, you'll create full-stack web applications, integrating server-side logic and front-end technologies, preparing you for real-world web development tasks. For example, you might build a web application that allows users to view and interact with your virtual zoo online.
Lastly, you will gain insights into implementing generative AI tools for task automation, further expanding your skills and keeping you at the forefront of modern software development. For instance, you might learn how to use AI to automate the generation of animal feeding schedules based on various factors. Throughout the program, you'll use tools and techniques that are standard in the industry, preparing you for real-world software development challenges. Get ready to dive into Java programming and build something amazing with your newfound skills.
So gear up, grab your laptop, and let's make some magic with Java. Who knows what you'll build? To be successful in this program, having some coding experience can give you a head start, but it's not a must-have. We recommend having a fundamental grasp of programming concepts and an openness to learn and develop your skills. The demand for software development professionals is on the rise. The United States Bureau of Labor Statistics anticipates a 25% increase in jobs by 2032. In today's digital age, software drives innovation across industries, making foundational software development skills essential for career advancement and success.
Join us to gain a competitive edge in securing software development internships or advancing your technical skills within project teams. Amazon, known for its innovation and technological leadership, brings a wealth of practical knowledge to this program. Amazon software developers are instrumental in creating customer experiences, designing architecture, and implementing products used by millions worldwide. By partnering, Coursera and Amazon leverage their respective strengths to create a powerful learning experience for aspiring junior software developers. This collaboration combines Coursera's flexible, high-quality content and interactive learning experience with Amazon's real-world technological expertise.
The primary advantage lies in acquiring practical skills and knowledge essential for launching a career as a junior software developer. This professional certificate not only equips you with the expertise needed for entry-level roles, but also provides a recognized certification, bolstering your credibility within the industry. This credential can significantly enhance your prospects for securing internships or apprenticeships, offering hands-on learning experiences under the guidance of seasoned professionals. On completion, you'll possess the skills and knowledge needed to develop software applications independently, troubleshoot technical issues, and collaborate effectively in software development teams. Additionally, you'll receive a professional certificate that can bolster your resume and career prospects in the tech industry.
Wondering what makes this program stand out? Here are some unique features that will benefit you. Online assessment preparation. Get ready to excel in online technical assessments used by top companies in their job interviewing process. Insights from Amazon software developers. Gain valuable first-hand knowledge and practical insights directly from seasoned Amazon software developers.
Embark on your journey to a rewarding career in software development with a program that equips you with the skills and knowledge needed to succeed in the tech industry. Get excited, get started, and get ready to make your mark in the world of software development. Imagine developing a calendar application that needs to store data for every day of the year. Creating a variable for each day is possible but inefficient. So how can you do it efficiently? In this video, you will learn about arrays, a basic data structure for efficient data management, memory optimization, and writing clean, maintainable code. An array is a fixed-size linear data structure that stores elements of the same type in a single container. They can be one-dimensional or multi-dimensional, but let's focus on a one-dimensional array for now. A one-dimensional array is like a list of elements, all of the same type, arranged in a single row. You access each item using a single index, such as days of the week. Crucially, these indices start from 0. Earlier in the video, you learned that creating a variable for each day of the month or year is possible but inefficient. Here's why. Declaring 31 separate variables for each day of the month means writing many repetitive lines of code, which would entail updating variables multiple times. Additionally, it could incur possible scalability issues if you need to introduce other variables such as months or years. And finally, it would reduce code readability and increase the chance of making errors. So instead of creating separate variables, you can use an array. Declaring an array in Java allows you to create one variable with many values. This method manages memory efficiently and adds flexibility. Let's explore how to declare a string array. The keyword string defines the data type, and the square brackets indicate an array. In this example, the word string is followed by square brackets, while the variable, days of week, instructs Java to create a string array without specifying its size or values. You can also declare an array with square brackets after the variable name. In this example, the word string is followed by the variable, and then the square brackets. There are two main ways to initialize an array, statically and dynamically. Let's start with static initialization. Consider a scenario where you want to represent the days of the week. The easiest way to create this array is by using an array literal, which allows you to define the values directly while declaring the array. This method is known as static initialization. In this code, the array days of week is initialized with the days of the week using curly braces, with each element separated by a comma. This approach is ideal when you know all the elements you want to include in advance. Now, suppose you want to create an array for the days of the week, but plan to add the days dynamically, perhaps filling the array later in your code. In this case, you would use dynamic initialization. Here you declare an array with a specified length and then assign values to each element as needed. This method is particularly useful when the elements of the array are not all known at the time of declaration or need to be computed or retrieved from another source. Let's extend the idea of dynamic initialization with the days of the week example. Suppose you want to create an array to hold the names of the days dynamically, using a loop to fill it. Here's how you could do it. In this code, the days of week array is created with a length of 7. Then, using a loop, each element of days of week is populated with the corresponding day from the days array. In this example, an empty array called positive numbers is created. Then a loop is used to fill it with values. Let's now explore how to access arrays. You can access elements through the index or by iterating over the array using a loop. Remember that indices start at 0. Let's start with using an index. You can easily access the required element when you know the position or index number. For example, to get the first element of the days of week array, use days of week and 0 in square brackets. This will return Monday. For the fourth element, use days of week 3, which returns Thursday. If you want to access an array's last element and don't know its total length, just pass the length of the array minus 1. In this case, it will be days of the week minus 1, all in square brackets. Remember, the square brackets indicate the array. The loop is the most suitable option for accessing all elements in an array because it lets you go through each item one by one without writing the same code again. For example, if you want to print each day of the week, you can use a loop to iterate through the array. Arrays help manage data efficiently, optimize memory, and write cleaner code. Think back to the calendar application. Using an array, you can store all the days of the month in a single structure, making it easy to access and update each day. Arrays can help you manage data structures like calendars more effectively. They provide a simple way to handle large sets of related data, reducing the complexity of your code. As you continue to explore Java, you'll discover robust data structures and algorithms that will elevate your coding skills. Arrays are your first step on this journey. Imagine using a calendar application that prevents you from creating new events. This would be very frustrating for your users. Applications like this must be able to modify and manage their data effectively to function well. Arrays are a fundamental way to handle such data, but you need to know how to perform operations on them to make the application usable. In this video, you will learn how to perform 3 primary operations on arrays: traversal, insertion, and deletion. Let's start with traversal. Consider the calendar application again. Imagine you'd like to browse different days, weeks, or months to view your schedule. Traversals allow you to navigate your schedule and find out what's planned. It is the process of going through each element in the array one by one. It is a straightforward process and is typically achieved using loops. Here's how it works in Java. Declare an array of strings named day of week. The curly braces initialize the array with the values Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Then a single line comment explains the code related to initialization. You initialize a for loop by declaring and initializing the control variable I, which starts at 0 and continues to iterate as long as I is less than the length of the day of week array. In each iteration, I is incremented by 1. Finally, print out the current element of the array. Now let's explore insertion. Suppose you want to add new events to specific days and times. Without insertion, you won't be able to schedule anything. Insertion refers to adding a new element to a specific index in an array. However, inserting an element into an array can be challenging because arrays have a fixed size. Insertion can be approached in 2 ways, either by adding elements without changing the array size or modifying the size to accommodate new elements. For example, if a calendar app uses a fixed-sized array to store daily events, you must know how to add new events without exceeding the array's maximum capacity. This ensures efficient scheduling within the array's predefined size. On the other hand, if the array needs to hold more appointments than expected, resizing the array dynamically keeps the application flexible and responsive to user needs. Let's explore an example. Imagine you've defined an array with a fixed size of 7 for 7 days of the week and want to insert an element at index 3. Since the array doesn't require altering its size when the insertion index is within the size limit, an element can be inserted without changing its size. You can now modify it with a new element. In this case, replace Thur with Thursday. Now imagine you have an array with 5 months of the year and need to add another month. This requires increasing the array's size. The position where you insert the new element, beginning, end, or middle, affects how you rearrange the existing elements, because inserting at the beginning or middle requires shifting elements to make space, while adding at the end does not. Finally, let's consider deletion. Deletion refers to removing elements from the array. Unlike modification, deletion affects the array size, because traditional arrays are not dynamically resizable. As a workaround to maintain the original array size after removing an element, you can replace the specific element with null. This keeps the overall size of the array unchanged. But what if you want to delete an element by altering the array size? In this scenario, like insertion, you would create a new array and copy all other elements except those you want to delete. Don't worry about that logic just yet. Simply understand that a new array is created and elements are copied one by one using a loop, excluding the element at the index you want to delete. Working with arrays is an essential skill for programmers. Here are a couple of key points to remember when working with arrays. Inserting or deleting elements in the middle of an array requires extra memory, which is not always the best solution. Deleting and replacing elements with null values can waste memory because the array size remains unchanged. If not appropriately handled, this can lead to null pointer exceptions. Later in the course, you will learn more efficient programming techniques to avoid these issues. Mastering these array operations ensures you can build robust applications when you enter the professional world. Imagine you're buying tickets to a highly anticipated movie online. How does the system show you which seats are available in real time, even as hundreds of others are trying to buy tickets at the same time? This magic happens with the help of arrays. You've already learned how to declare, initialize, and manipulate arrays, but now let's understand where they truly shine in everyday scenarios. In this video, you will learn the specific use cases for arrays using real-world examples. They include data collections with fixed sizes and when efficiency and memory management is required. Think about the calendar application you've been working with. When building such an application, you would need to keep track of dates, weekdays, and events throughout the month. To build it efficiently, you'd use arrays. An array can hold the days of the week, making it easy to access any specific day. For example, if you want to find the third day of the week, you simply use days of week. And since arrays always start from 0, days of week at position 2 will give you Wednesday. Consider the scenario we introduced at the beginning of the video, buying tickets online. How can arrays be used if, say, only 100 seats were available? How do you track which seats are available and which are booked? With an array, of course. Each seat corresponds to an index in the array. For instance, seat 0 is the first seat, seat 1 is the second, and so on, up to seat 99 for the 100th seat. If you want to check if seat 50 is free, just check seat 49. Arrays provide an efficient way of handling data because they store elements close together in memory, making it quick to access any item. Plus, they don't waste space. Each element has its spot. Here's an example to illustrate this. Let's say we're building that calendar application, and in Java, you've written a string array with days of the week, Monday to Sunday. To find Thursday, you simply use days of week at index 3. Remember, arrays start at 0, so index 3 gives you Thursday. Efficient, right? Now let's apply this to the seating example. How do you choose the right data type for the seats to minimize memory usage? You could use an array of integers or booleans. An array of integers might seem like an easy choice, where each integer shows whether a seat is empty, indicated by 0, or occupied, indicated by 1. But keep in mind that each integer usually takes up 32 bits or 4 bytes of memory. If you have a lot of seats, this can use up a lot of memory quickly. On the other hand, using a Boolean array is much more memory efficient. A Boolean only needs 1 bit to show 2 states, true or false, representing whether a seat is occupied or empty. So, using a Boolean array can save a lot of memory compared to using integers. Each element represents a seat. For example, seat 0 is the first seat, and seat 1 is the second, and so on. If you need to check if the seat number 60 is available, just check at seat 59. So, why are arrays preferred in these scenarios? First, they have a fixed size. This makes them perfect for applications like a calendar or a seating chart, where the number of elements doesn't change. In other words, their positions are fixed. This makes your code clean and efficient, especially when looping through each day to display events. Arrays are also easy to access. Each element has a specific placement, so finding any item is fast. This is crucial for performance-critical applications, where quick updates and checks are necessary. And finally, arrays are efficient. They store elements close together in memory, which means accessing or updating any element is quick. This makes them ideal for applications that need to run smoothly and efficiently. To sum up, arrays are ideal for managing static collections of elements, like the days of the week. They are fixed size, easy to access, and efficient regarding memory and performance. So, next time you're building an app that needs to store a fixed set of items, remember the power of arrays.
Hi, my name is James Karai. I'm a software engineer at Amazon. A normal day for me is a lot of coding, a lot of code reviews, and a bunch of meetings. And the meetings are all kinds of things like design reviews, planning for future projects, mentorship and career development, things for the people I mentor. For my team, the tools and technologies that we use are Java and Python, for sure. Those are really important for our tech stack. And also, of course, being at Amazon, we use AWS technologies extensively. Beyond that, we have the freedom to use whatever tools we need to debug and assess and research, which makes the days very interesting for sure. I think My biggest advice for people that want to get into the field would be make sure you're doing it because you're interested in it. Today, there are millions and millions of software engineers at all different kinds of levels of involvement. So people can learn really high-level technologies and not understand the lower-level implications. So it can be really overwhelming if you want to break into the field. Like, do I have to learn everything, or what's important? But if you're not interested in getting into the weeds, I think it'll never be fulfilling as a job. So that's really important. Staying up to date with the latest technologies is one of the biggest challenges of being a software engineer. So much of our job is reading documentation and making sure we have the latest version, or we're up to date with the most proper tool for the task. A big part of that is just the day-to-day job. So it's okay to spend your work time learning new things and staying up to date with the latest updates to the tools you have. Mentorship's super important in software engineering everywhere, as well as it's a priority at Amazon. So for me personally, I'm a mentor to junior engineers and to interns. The biggest thing I've learned from mentoring is that everybody needs support in different ways. Some people need technical advice, how to make design decisions, which are tough to know the answers to if you've never gone through the steps. So for me, it's trying to understand, okay, do people need more support, or should I give them some space to figure things out for themselves? At a big picture view, software engineering and the products of software engineering are ubiquitous in the modern landscape. So more than just big tech companies, right? Almost everything that we interact with on a day-to-day basis is some product of software engineering. As a result, it's important for software engineers, both leaders of industry and regular people working on these products, to take stock of that and to be good stewards of society as we build products that people use every day for little things like opening their garage and making sure their fridge works, right? As well as big things like running a large tech service that companies rely on. I think some of the toughest projects that you work on as a software engineer are the ones where you don't expect them to be so tough. So you maybe underestimate the scope, or things change, midway through. Every project has its obstacles to overcome, but the most important thing is making sure to communicate with stakeholders and to roll with the punches, really.
Think about organizing a train journey with friends. Each stop is carefully planned, and the train follows a specific route, moving systematically from one station to the next. Just like in a well-organized trip, each step in this journey needs to happen in a specific order to ensure everything runs smoothly. This concept of ordered movement helps illustrate how linked lists operate in programming. This video will cover the basic concept of a linked list and how it organizes data. It will explain the differences between singly and doubly linked lists and demonstrate how linked lists offer flexibility and efficiency in managing dynamic data. So what exactly is a linked list? A linked list arranges information in a sequence, similar to stations along a train route. However, instead of stations and tracks, a linked list is made up of nodes and their connections. In programming, linked lists provide a flexible way to manage data, allowing for easy insertion and removal of elements without rearranging the entire sequence. In a train journey, the train departs from the first station and continues to the next, progressing through each station until reaching the final stop. Similarly, in linked lists, each node follows the sequence like a station along a flexible path. Each node holds data and a reference to the next node, much like the station has a name and details about the next stop. Each node consists of one or more data parts, taken to be a single data unit, and one reference part, in case of a singly linked list, or two reference parts, in case of a double linked list. These references are sometimes referred to as pointers, since they point to another node. This structure maintains the sequence, ensuring it stays intact and efficient. Assume that each station master, or head of a station, knows only about the route to the next station and gives this to the train driver on reaching a station. If this is the case, then the train journey to travel among the different stations is a fitting example of a singly linked list. In a singly linked list, each node is aware only of the next node in the sequence. Once a train leaves a station, it no longer interacts with the previous stops. This one-way flow is what characterizes a singly linked list. On this journey, there's no turning back, only moving forward to the next node in the sequence. Doubly linked lists, in contrast, resemble a route where both the station master, or head of the station, has information on both the next and previous stations. Each node has two pointers, one pointing to the next node and the other to the previous one. This two-way connection enables movement in both directions, making it easier to navigate the list or make changes from either end. Note that the first node's previous pointer will typically be null, as there's no node before it. So, why use linked lists instead of something simpler like an array? The advantages that linked lists offer over arrays are dynamic size or flexibility, and efficiency in insertions and deletions, no wastage or shortage of memory, all of which are important when manipulating sequences of data. For instance, if you need to add a new station to the planned route at the last minute, it's similar to inserting a new node into a linked list. An array is like having all the stations on the route lined up in a fixed order, so adding a new station would require shifting all the others to make space. This process can be time-consuming and disruptive. With a linked list, you can simply update the references in the nodes. This makes manipulating linked lists quicker, easier, and less disruptive to the overall sequence. If you're working with a list where data is frequently added or removed, linked lists are an ideal choice. Take, for example, a playlist of songs where tracks are regularly added or removed. With a linked list, you can effortlessly insert a new song at any point in the playlist, without needing to rearrange the entire list. Another example is a to-do list app, where tasks are frequently added and completed. A linked list efficiently manages these tasks, allowing you to easily insert a new task in the middle of the list or remove one when it's completed. More specifically, single linked lists are ideal for situations where data needs to be processed in one direction, such as handling a queue of tasks, where each task must be completed in sequence. On the other hand, doubly linked lists are well suited for scenarios where you need to move in both directions through your data, like moving backward and forward among the train stations. To recap, a linked list is comparable to a well-organized train journey. Each node, or station, holds data and has a reference to the next stop. In singly linked lists, each node only knows about the next one, whereas doubly linked lists reference both the next and previous nodes. Understanding linked lists gives you a powerful tool for efficiently managing dynamic data. Whether it's a playlist, a to-do list, or any other data sequence, linked lists help you handle changes smoothly and keep everything running efficiently. Array lists are like a flexible to-do list. But what if you need to organize data in a strict sequence, moving only forward? This is where singly linked lists come into play. Picture a train trip across several cities, each connected in a straight line. Just as you move from one city to the next in sequence, a singly linked list in programming advances from one station or node to the next in a specific order. If you and your friend are traveling on the same route, but his travel route terminates 3 stops before yours, then you would have to have different linked lists, unlike a train where you can travel by the same one till the cities match. This means that if you are storing the names of cities in a linked list, and if the sequence is different, then the linked list must be different. In this video, you'll explore the structure of singly linked lists, how they're manipulated, and how they're implemented in Java. First, a singly linked list is a data structure where elements are arranged in a linear sequence. But unlike arrays, they aren't stored in consecutive memory locations. In a linked list, memory allocation is done only when a new node is added, which could be anywhere in the memory available. The operating system will decide where memory is allocated, which could be in a non-continuous location from the previous node. This is why you need a link to point to the next or previous allocation to access that area's value in memory. Each node has 2 key components, data and next. Data is the value stored in the node, like a city's name. Next points to the following node, similar to the next city on your train route. The first node, called the head, acts as the entry point to the list. Each reference, pointer, or link connects one node to the next, except the last node, which points to null as a reference. This indicates that there are no more items in the linked list. The term null means undefined, and in the case of linked list, signifies the next node is undefined or unavailable. Similar to planning a train journey by connecting each city or landmark, working with a singly linked list involves declaring and linking each node, creating a path from one stop to the next. To begin your journey or list in Java, you must first define each stop by creating a node class. Each node stores essential information, such as the data, the name of the city, and a reference to the next stop. Once your nodes are defined, you need a way to manage your journey. This is where the linked list class comes in. It acts as the starting point, with the first station, the head, leading the way, and each stop linked to the next, guiding you to the end. To initialize a singly linked list, create an instance of the linked list class. When you create the linked list, it will initially be empty. Since it is empty, there are no references to point to, so you can set the head node to null using the this keyword. With your node and class set up, building a linked list is like planning a train journey across several cities. Your route is mapped out, but plans can change. You might add a city, skip a stop, or update a destination. A singly linked list lets you manage these adjustments seamlessly. Suppose you discover a city you must visit and want to add it to your journey. In a singly linked list, this is like adding a new node. For example, imagine a planned train route that goes from New York to Richmond and then directly to Washington. If you want to add Philadelphia to your journey, placing it after Richmond but before Washington, here's how it works. First, create a new node for Philadelphia. Next, adjust the links by connecting Richmond to Philadelphia instead of directly to Washington. Finally, link Philadelphia to Washington. Your journey now flows smoothly from New York to Richmond, adds a stop in Philadelphia, and continues to Washington without disrupting the other stops. In Java, adding a new node to a singly linked list involves updating the next reference of the preceding node to point to the new node, keeping the sequence intact while accommodating the change. If a stop no longer fits your travel plans, you can skip it. Suppose you decide to skip Philadelphia. You must remove the respective node from your linked list. Observe that Philadelphia is a part of the route because New York points to Philadelphia, which in turn points to Richmond. What if New York directly starts pointing to Richmond? Philadelphia will automatically be removed from the route. So, in a linked list, you identify the node to be removed and update its previous node's reference to point directly to the next node. The unwanted node is left out, keeping your journey smooth. So, instead of stopping in Philadelphia, you directly travel from New York to Richmond. With this adjustment, your train travels smoothly from New York to Richmond and continues to Washington. Removing Philadelphia simplifies your trip, allowing you to focus on the key destinations. This quick modification keeps your journey streamlined and aligned with your preferences. When you update the previous node's reference to remove a node from the singly linked list, remember that the removed node is no longer pointed to by any node. It means the removed node is dereferenced and cannot be accessed. If you want it back, you must create it again. But what if a stop changes? You visit a different part of the city or the destination name updates. In that case, you'll need to update the waypoints in your journey. In a linked list, this means simply updating the data in the corresponding node to reflect the change. Initially, your route starts in New York, stops at Richmond, and then heads to Washington. Remember, each city is a node, with data representing the city's name and next showing the link to the next city. To update it, locate the node containing Richmond and change its data to Philadelphia. Note that currently a node's data only contains city names, whereas in a real-life scenario, a node representing a city might contain detailed information, such as city name, population, and coordinates. In such a case, the singly linked list behaves the same, except that the node now has more than one data point. Your journey adjusts accordingly. Now it starts in New York, stops at Philadelphia, and continues to Washington. This update demonstrates the flexibility of singly linked lists in managing dynamic data without needing to restructure the entire route. In this video, you've explored how linked lists work conceptually and in Java. A singly linked list is like a train journey, where each city is a node and the tracks between them connect you from one city to the next. The node of a singly linked list might contain data about anything, not just city names or detailed data points. This gives you the power to store a collection of objects together as a single entity, the singly linked list. This simple yet powerful structure enables efficient management of data sequences, whether you're handling a short list or a long chain of data. Just like a train journey where each stop is essential, every node in a singly linked list plays a crucial role in guiding you through your data efficiently and effectively. If trains could only ever travel in one direction, missing your stop would be disastrous because there's no way of returning. Thankfully, cities along a route aren't configured like singly linked lists, which can only move forward. Instead, they're more like doubly linked lists, allowing movement to the next and previous stations. In this video, you'll learn all about doubly linked lists. Specifically, you'll learn how to visualize, implement, and modify them in Java. You'll also learn essential operations like adding, removing, and updating nodes. A doubly linked list is advanced because each node links to the next and previous nodes. Each node is a fundamental part of a more intricate structure compared to a singly linked list. This dual link system makes data management much easier. They have three main components: data, which stores the information or value at that node; next, which is a link to the next node in the list; and previous, which is a link to the previous node in the list. Let's take this into Java now. Here's how you declare a node in Java. First, define a node class representing a single element in a doubly linked list. After declaring it, the constructor initializes a new node with the given data and sets the next and previous references to null, meaning the node does not yet point to any other nodes. The constructor initializes the doubly linked list by setting the head to null, starting the list as empty. Adding a node in a doubly linked list is like inserting a new stop on your train route. You must update the connections in both directions. Let's add a node in the middle, assuming you're traveling across several American states. When adding a new node between two existing nodes, set the new node's previous reference to node 1. Then, set the new node's next reference to node 2. Update node 1's next reference to point to the new node. Then, update node 2's previous reference to connect it to the new node. What if you wanted to add a new stop at the beginning or end of the train route? Regarding a doubly linked list, this would mean adding a node at the start, also known as the head, or at the end, known as the tail of the list. Let's add a node at the head, where your train journey begins. You'd like to start in Los Angeles instead of New York, so first set the LA node's next reference as the current head. Then, update the original head's previous reference link to the new node. Finally, update the head of the list as the new node and set its previous reference to null. Now, if the final destination on your route changes, you can set the new stop's previous reference to the current tail. Then update the current tail's next reference to link to the new node. Finally, update the tail of the list as the new node and set its next reference to null. What if a stop no longer fits your travel plans? Thanks to the train's ability to move in both directions and the bidirectional nature of doubly linked lists, you can easily adjust the route. In this case, it means removing a node. If the stop you're removing is in the middle of your journey, you'll need to reroute the tracks. First, update the next reference of the preceding node to point to the node after the one you're removing. Then, update the previous reference of the following node to point to the node before the one you're removing. The node you wanted to remove is now disconnected from the list, and the surrounding nodes are directly linked, maintaining the list's integrity. Since no node refers to the removed node, the next node takes its place. Now, if the city you're removing is the first stop, you'll simply start your journey from the next city, ensuring there's no track back to the old start. Similarly, if you're removing the last stop, you'll end your journey at the city just before it, cutting off the track to the removed stop. This keeps your trip smooth and uninterrupted, even with the changes. Let's start with the head. First, update the head as the next node in the list. Then, set the new head's previous reference to null to ensure no link to the removed node. Next up, the tail. First, update the tail as the previous node in the list. Then, set the new tail's next reference to null, cutting off the link to the removed node. The route now ends at Philadelphia, removing DC, node 3, from the list. Finally, let's explore traversal. In a singly linked list, traversal is a one-way street. You can only move forward from the head to the tail, following the next references. If you need to revisit a previous node, start over from the beginning. In contrast, a doubly linked list offers more flexibility. For forward traversal, start at the head and follow the next links until you reach the end, where next is null. For backward traversal, begin at the tail and follow the previous links back to the start. If the previous or next reference is null, then you know you're on either the first or the last node. This bi-directional capability allows you to move freely through the list, making updates and navigation much more efficient. In summary, the doubly linked list offers significant advantages over the singly linked list, especially in scenarios where bidirectional traversal is necessary or preferred. Whether revisiting previous data or managing elements in the middle of the list, doubly linked lists provide a powerful tool for complex data management. Understanding the basic structure and functionality of doubly linked lists enables you to handle a wide range of programming challenges as you continue to grow as a software developer. Imagine you're the manager of a book club, and every book that the club plans to read is like a link in a chain, one after another. Your task is to keep track of this lineup of books in a way that lets you add new ones or go back to older ones without any fuss. This situation is a lot like using lists in program linked lists, which come in two types, singly linked and doubly linked. Every month, the club picks a new book to read. But as the club grows and members want to revisit old favourites or insert a particular book into the middle of the lineup, you realise you need more flexibility. That's where a doubly linked list becomes useful. Instead of just linking to the next book, each book in the list is connected to the book before and after it. This setup allows you to easily move through the list in either direction, making it simple to revisit old books or insert new ones wherever needed. In this video, you will learn about the differences between singly linked and doubly linked lists in terms of operations such as insertions and modifications, traversal, and memory usage. Let's begin with insertions and modifications. For a singly linked list, adding a new book after the current read is easy. You simply attach a new note to the last book. However, if you need to insert a title earlier in the sequence or between two existing books, the process can be cumbersome, requiring a traversal from the start to the insertion point. This code adds a new book to a singly linked list right after the specified previous book node. It creates a new node, new book, links it to the node that follows, previous book, and then updates previous book to point to this new node, effectively inserting the new book into the list. With a doubly linked list, inserting a book anywhere in the lineup is more intuitive. You can easily slot a new book between two others, updating the pointers for both the preceding and following books. This flexibility is invaluable for accommodating special events or thematic inserts. This code inserts a new book into a doubly linked list right after a specified book, previous book. It creates a new node, new book, with the title, then updates the pointers so that the new book connects properly to the next book in the list and the previous one. If there's a book after the previous one, its prev pointer is adjusted to point back to the new book, ensuring the list remains correctly linked. Next, let's explore the differences between singly linked and doubly linked lists in terms of traversal. With a singly linked list, if members want to know what the next month's book will be, they simply check the note on the current book. This one-directional flow and traversal in a singly linked list is straightforward, but is limited to moving forward. The code current.next updates the current variable to point to the next node in the list. By doing this, the loop can move to the next book in the sequence during the next iteration. With a doubly linked list, should the club decide to revise a previous selection or look ahead, members can easily navigate in either direction. This capability is useful for planning anniversary reviews or thematic months, where past and future reads need to be coordinated. Imagine you're browsing through a digital bookshelf and the Navigate Books function is your guide. It first looks at the current books by grabbing its title, current.booktitle. Then it checks if there's another book ahead, current.next. If there is, it notes the next title. Otherwise, it says no book selected. Similarly, it glances backward to see if there's a previous book, current.prev. If there is, it grabs that title too, but if not, it tells you this is the first book. Now that you've examined the differences between singly linked and doubly linked lists in terms of traversal, let's explore memory usage. Choosing the right data structure can often feel like deciding on the best organizational system for a large, evolving project. To better understand this decision, let's revisit our book club analogy. Memory management is critical in Java because it directly impacts the application's performance and scalability. Every node in a linked list is an object, and each object consumes memory, not only for the data it holds, but also for the pointers or references, and some overhead by the Java Virtual Machine, or JVM, for object management. Now let's gain insight into the memory composition of nodes, starting with singly linked lists. Each node in a singly linked list contains the data, for example, the book title, which can vary in size depending on the data type, and a single pointer to the next node. Similar to a singly linked node, a doubly linked list contains the data and a pointer to the next node, but it also contains a pointer to the previous node. Let's analyze the memory implications for each type of linked list. The extra 4 bytes, 32-bit JVMs, in the doubly linked list nodes for the prev pointer might seem trivial, but in large-scale applications where millions of nodes might be involved, this additional memory usage can add up significantly. Let's conclude by examining the trade-off between using singly and doubly linked lists in Java. Singly linked lists are memory efficient. They only need to move forward through the data. They are efficient for insertions and deletions at the beginning or in the middle of the list. They are preferred in scenarios where memory resources are limited and need to be conserved. And finally, they are suitable for applications that process data sequentially. On the other hand, doubly linked lists are preferred when you need to move both forward and backward through the data. You need to easily add, remove, or access items from both directions. The data list is often updated with additions or deletions. The application involves more complex data handling, and data elements naturally connect in both directions, like in navigation systems. In this video, you learned that choosing between singly and doubly linked lists in Java is similar to managing your book club's reading list. If you only move forward from one book to the next, a singly linked list works well, simple and efficient. But if your club revisits old reads or inserts new ones in specific spots, a doubly linked list, like a flexible book lineup, allows easy movement in both directions. In application development, this decision isn't just about memory, but also how you manage and navigate your data. Understanding these trade-offs helps you make smarter choices that improve performance and user experience. Linked lists require dynamic management to be effective. This includes modifying, searching, updating, and deleting elements, all operations that are crucial for maintaining a list. In this video, you'll learn how to insert new nodes at different positions in both singly linked and doubly linked lists. Think of developing a program that reorders a book club's reading list as new books are added. For example, true crime thrillers, always a hit, go straight to the top of the list. Sequels get slotted in the middle to keep the story fresh in everyone's mind. Everything else? Well, they usually find a place at the bottom of the list. Let's explore how to manage these types of insertions in both singly and doubly linked lists. Let's start with a singly linked list, where each node only references the next one. Imagine adding a new book, the latest true crime novel, to the top of your reading list, making it the first book everyone reads. In a singly linked list, inserting at the beginning is straightforward. Create a new node, set its reference to the current head, and update the head to this new node. This operation is useful because it allows fast insertion at the start, ensuring quick access to the most important or recent elements. Doubly linked lists differ from singly linked lists in that each node references both the next and previous nodes, enabling traversal in both directions. To add a node to the top of a doubly linked list, link the new node to the previous head, ensuring the list remains bidirectional. Update the previous link, and then update the head to the new node. The new book is now placed at the top, and the previous top book knows it's been moved down, thanks to the extra pointer. Now that we can add an item to the top of a linked list, how do we handle the bottom? Most books will fall in here, So to insert at the end of a singly linked list, simply traverse to the last node and link the new node there. This is like adding a new book to the end of your book club's reading list, where it patiently waits its turn to one day be read. In a doubly linked list, as before, find the last node and link it to the new node. Then link the new node back to it. Done. The new book is added to the end where it belongs. And once again, the program knows here which book precedes it, so the bidirectional navigation is maintained. Many of a year's book releases are sequels or part of a series, making them ideal for the middle of the reading list. Inserting a node in the middle of a singly linked list involves finding the right spot and updating the pointers. So, just create a new node, link it to the next one, and then link the previous node to the new. Simple. When a new entry is added, the other entries are automatically pushed down. In a doubly linked list, both the next and previous pointers of the surrounding nodes need to be updated when inserted in the middle. The previous node's next link is updated to point to the new node, and the next node's previous link is updated to point back to the new node. The reading club will get to these entries eventually. The operations explored here were for both singly and doubly linked lists and can be applied to all your future projects. In general, choosing between these two structures depends on your specific needs, whether you prioritize memory efficiency or flexible navigation. In this video, you've learned how to perform insertion operations in singly and doubly linked lists, specifically adding nodes at the beginning, middle, and end. Implementing these simple yet powerful operations will enhance your ability to manage various data structures in future projects. Imagine curating a digital photo album with hundreds of unforgettable moments. You want to organize these photos in a way that allows you to access, add, or remove any image quickly. How you store them, whether in a structured grid like an array, or a more flexible chain like a linked list, affects how efficiently you can manage your album. But which approach is better? In this video, you'll learn about the time complexity of operations on arrays and linked lists to answer this question. You'll compare the time complexity of insertion, deletion, and traversal in both data structures. First, let's explore time complexity. It estimates the time an algorithm takes to run relative to the input data size and is expressed using big O notation, such as order of 1, order of n, order of n square, and so on. Imagine sorting through your photo album. Finding the one you want is easy if you have just a few pictures. But what if you had thousands? The time it takes to find a specific photo depends on how you've organized your album. Let's see how these concepts apply to arrays and linked lists. With arrays, accessing a photo is like knowing the exact slot in a photo grid where your picture is stored. If you see the index, like the position of a photo in a row, you can grab it instantly. This operation takes order of 1 time, meaning it's very fast regardless of the size of your album. In the code, you can observe reaching directly for the third photo in a photo album. You know exactly where it is, at index 2, so you grab it instantly without looking through the others. This operation takes the same amount of time, no matter how many photos there are. In a real-time scenario, each photo is linked to the next one, like a chain. You might need to start from the beginning and follow each link to find a specific photo until you get to the one you want. This can take order of n time because the more photos you have, the longer it might take to find a specific one. Imagine flipping through a photo album page by page until you reach the one you're looking for. You can observe, start at the first page, and move forward one by one. So the time it takes depends on how far you have to go, which makes it order of n time complexity. So which one is better? The answer lies in the requirement. Arrays are the clear winner for quick access to any photo. They are also more efficient if you frequently need to find a specific photo based on its position. However, linked lists can be slower since you might have to traverse many images. Inserting a new photo into an array, especially in the middle, can be cumbersome. You might have to shuffle all the images to make space. This shifting takes order of n time because each photo might need to be moved to accommodate the new one. Suppose you're making space for a new photo in the middle of the array, which requires shifting the existing photos one slot over. The time it takes grows with the number of photos, making it an order of n operation. However, inserting a new photo in a linked list is more flexible. Adding the photo at the beginning or end is as simple as updating a link, which takes order of 1 time. If you need to insert it somewhere in the middle, you'll first have to navigate to the spot, which takes order of n time in the worst case. But once you're there, the insertion itself is quick. So now, think about this scenario and decide, which is better? If you frequently need to insert photos at specific positions, linked lists are more flexible and can be quicker for these operations, especially when inserting at the start or end. Arrays, while faster for access, can become inefficient when inserted in the middle. Deleting a photo from an array is similar to inserting one. You might need to shuffle the remaining photos to close the gap. This also takes order of end time, as every photo after the deleted one has to be moved. In the code, you can observe that it shifts the remaining photos to the left after deleting one in the middle, moving each subsequent photo over. The time it takes depends on the number of photos, making it an order of n operation. Deleting a photo from a linked list can be more straightforward. If it's at the beginning or end, you simply update the links, which takes order of 1 time. However, like with insertion, if the photo is somewhere in the middle, you first need to find it, which can take order of n time, but the deletion itself is quick once you're there. You can remove a photo by simply skipping over it in the chain, directly connecting to the next one. It's quick and takes constant time, so it's an order of 1 operation. Which one do you think is better? Linked lists generally offer more efficiency for deleting photos, especially if deletions are frequent and not always from the middle. Arrays require more effort because they require shifting elements around after a deletion. In this video, you explored the time complexity of arrays and linked lists. You learned that arrays offer quick access to specific items, but are inefficient for adding or removing items, particularly in the middle. On the other hand, linked lists are more flexible for frequent additions or deletions, especially at the ends, though slower for specific item access. Choosing the right data structure based on your needs is crucial, as no one-size-fits-all solution exists. Informed decisions will lead to more efficient and effective code as your projects become more complex. Imagine building a music application that catalogs thousands of songs from hundreds of artists. With such a large amount of data, quickly retrieving information on specific artists or songs is essential for a good user experience. Suppose a user wants to find the artist for a particular song. One approach is to create a large array of song objects to store the song titles and artist names. Then, starting with the first element at index 0, look at each song object in the array until you find the song you're looking for. However, because the application contains thousands of songs, searching for the right song will take a long time, which could frustrate your end users. A better solution is a HashMap, which rapidly locates items in large data collections and is much faster than searching an array. In this video, you will learn the basic concepts of the HashMap type and the benefits of using it when you need to find information as quickly as possible. Before you learn about HashMaps, it helps to understand the concept of an identifier, because they are fundamental to how HashMaps efficiently store and retrieve data. An identifier is a string of characters or numbers that uniquely identifies a person, place, or thing. For example, when using social media, you have a username that is unique to only you. That username is an identifier. So what is a HashMap exactly? A HashMap is a collection of key-value pairs. A key is a unique identifier of some kind, such as your username or national ID number. A value is the information associated with that identifier, such as your social media profile or personal information in a national database. How can a HashMap be used in your music application? Each song in the music application has a key and a value. The key is the song's title and the value is the artist's name for that song. Consider the song Satisfaction by the Rolling Stones. In this instance, Satisfaction is the key and the Rolling Stones is the value. In other words, the song title is an identifier that can be used as a key, while the artist or band's name is the value. Now imagine if the application you're building contained 20,000 songs. There would be many songs and artists to keep track of, so you would need a HashMap to retrieve a song's artist as fast as possible. To demonstrate this, let's create a Java application called SongMap with a main method that can be executed from the command line. Import the HashMap type from the java.util package by typing import java.util.hashmap. Remember that because HashMap is a Java class, it uses camel case for its class name. The next step in the body of the main method is to create an instance of the HashMap type. To do this, create a variable called map of type HashMap with the new keyword and a HashMap no argument constructor. This line of code creates an instance of a HashMap. Once the HashMap instance is created, you can add song titles and artist names. To do this, use the put method, which requires two parameters, the key and the value. In this case, the song title is the key and the artist name is the value. The type used for the key and value are both string types, but they do not have to be. Keys and values can be different class types. Add a print statement to put the contents of the HashMap. Finally, run the Java application so it will print out the contents of the HashMap instance, which should display the song titles and artists like this. Notice that an equal sign separates each key from its value. In this case, the song title and its artist, and that a comma separates each key value pair. This is the default print format for the contents of the HashMap type. You may also notice that the order of the songs and artists in the HashMap is not the same as the order in which they were entered. That's because a HashMap is not an ordered list like an array. The order in which you add items to a HashMap does not affect their storage order because HashMaps are designed for quick value retrieval, not for maintaining an ordered list. The keys used in a HashMap, in this case song titles, must be unique. Adding two songs with the same titles will result in the first artist's name being overwritten by the second. For example, if you add two songs titled LOVE as shown. The song LOVE with the artist, Alvin and the Chipmunks, will have the artist changed to Nat King Cole because only one artist's name can be associated with a song title. In this example, the assumption is that song titles are only associated with the original artist and that two different songs can never have the same title. In reality, the world is very different. Cover songs, where a song is a new recording by a musician other than the original, are common. However, for the purposes of our example, you are not considering cover songs. Let's go back to the example. After adding the song titles and their artist names to the HashMap instance, it's easy and quick to look up a song's artist by its title and print it. Here, the output from the print line will be Nat King Cole. This is correct. The song, LOVE, is no longer associated with Alvin and the Chipmunks. The entry's artist is now Nat King Cole, because you set the LOVE key to the value of Nat King Cole after you put in the LOVE key with the value of Alvin and the Chipmunks. HashMap instances are extremely fast at looking up values by their key. They use hash algorithms to convert the key into a value that can be indexed and quickly referenced inside the HashMap. Every instance used as a key must provide its hashed key to the HashMap. The built-in data types, such as java.lang.string and int, all have built-in hashcode value algorithms. It's also possible to create custom hash algorithms for the classes you create, which will be covered later in the course. In this video, you learned that a HashMap stores values in key value pairs and ensures that keys are unique. A HashMap is used to quickly and efficiently look up values by their keys. It is an excellent addition to your software development toolkit when dealing with large amounts of data. Imagine that the music application you're building needs to track thousands of songs. While you've mastered adding and retrieving key value pairs using a HashMap, there's much more you can do with it to enhance your application. Let's explore how. In this video, you will learn about some of the basic operations in HashMaps, including replacing values, checking for the existence of keys, getting the number of key value pairs, clearing the HashMap, and checking if the HashMap is empty. Let's return to the sample of songs and artists from earlier. Song titles such as Satisfaction and their corresponding artists such as the Rolling Stones are stored in the HashMap. Remember that song titles are unique to each song, meaning they are an identifier that can be used as a key. The name of the artist or band is the value. To demonstrate some basic operations of HashMaps, a Java application called SongMap imports the HashMap type and then creates an instance of a HashMap that uses string types for both the keys and the values. It then uses the put method to add a few song titles and artists to the HashMap instance. This should be familiar to you from the previous video. If you run the SongMap application, the output will look like this. Inside the curly braces, each song title and its corresponding artist's name. This is the default format when printing a HashMap. As you learned, if the put method adds a key value pair to an existing key, the HashMap will update the value. Let's update the song title yesterday to a new artist. The replaced value is returned if the put method updates an existing value. Running the program produces the following output. Initially, the HashMap contains the key yesterday with the value Ray Charles. When the put method updates the value to the Beatles, it returns the previous value Ray Charles. Now the map shows that the yesterday song title has the value of the Beatles. Returning the value previously mapped to a key can be useful when you are unsure what the original value was or need to do something with it, such as adding it to a different HashMap or logging the update. If you use the put method with a key that isn't in the HashMap, it will simply add it as a new key value pair and return null. The return value is null when the put value adds a new key value pair. So, if yesterday wasn't already in the HashMap, a new entry would be added, and the put method would return null. Another method that behaves similarly to the put method is the replace method. Let's change the put method call with the replace method call and see what happens. Running the program with the replace method call results in the same output as when the put method call was used. The method returns the value, Ray Charles, and replaces it with the Beatles for the key yesterday. However, the replace method behaves differently from the put method if it's called with a key that doesn't already exist in HashMap. The following attempts to replace the value mapped to the LOVE song title with the artist Nat King Cole. Running the program results in the following output. In this case, the value returned is null because the key LOVE doesn't exist in the HashMap. If the key doesn't already exist in the HashMap, the replace method doesn't modify the HashMap. The map has the same contents before and after the call for the replacement method. The replace method is useful when you do not want to add a new key value pair if the key isn't already in the HashMap. It will only update a value if the key is already present. You can check for the presence of a key using the contains key method. The contains key method returns a Boolean value. To demonstrate, the program tests for a key you know is in the HashMap and then checks for a key you know is not in the HashMap. Running the program results in the following output. True for testing for jump, but false when testing for LOVE. Knowing the number of elements in a HashMap is often helpful. For example, you could display the total number of songs in the music application to the user. The size method can provide this information. The size method returns an int value equal to the number of key value pairs in the HashMap. The print statement displays the size. The clear method removes all the contents from the HashMap. If you call the clear method and then print the contents of the HashMap, you get empty curly braces, signaling that the HashMap is empty. Finally, you can use the isEmpty method to test if the HashMap contains any elements. If the HashMap is empty, the method returns true. If it has at least one key value pair, it returns false. In this case, the output is true because you called the clear method and emptied the HashMap before calling the isEmpty method. In summary, the HashMap is a powerful key value collection that enables lightning-fast access to data using unique key identifiers. Beyond basic operations like adding and updating entries, it offers advanced features to conditionally replace entries, check key presence, count elements, clear all entries, and verify if the map is empty. As a staple tool for Java developers, mastering HashMaps will significantly enhance your ability to build efficient and dynamic applications, such as developing a music application that can hold large datasets. When managing large datasets, the data structure you choose can make or break your application's efficiency. While HashMap shines in certain situations, it's not always the top choice. In this video, you'll learn how to leverage HashMap by understanding its performance characteristics, common use cases, and trade-offs. A HashMap is like a digital dictionary where you store data as key value pairs. You can quickly look up a value if you know its key. For instance, you might store student IDs as keys and their names as values. But if keys or identifiers aren't important, you might be better off using a standard array, array list, or linked list. When you put a key value pair into a HashMap, Java uses a hash function to convert the key into an index in its internal array. This enables quick access later. When you call the get method, the HashMap hashes the key and goes directly to the corresponding index in its array. The average time to find, insert, or remove a key value pair in a HashMap is typically very fast, around 01. This means the time doesn't increase much as more key value pairs are added. However, if many keys hash the same index, operations can slow down, potentially to ON in the worst case, meaning the efficiency of the HashMap could be affected by the number of stored pairs. This is rare, but the HashMap can slow down when it happens. In order to know when to implement a HashMap, you'll need to understand how it uses memory and storage. To operate efficiently, HashMap uses extra memory and stores data in an array. A HashMap starts with a capacity of 16, meaning it can initially hold up to 16 key value pairs. Each time a HashMap exceeds its current capacity, it automatically doubles in size, requiring additional memory and processing power. With every instance of exceeding the capacity, the size continues to increase. In short, as you add more key value pairs, the array may need to grow, and this resizing consumes additional memory and time. The efficiency in storage a HashMap offers means it outperforms other collection types in certain scenarios. To better appreciate its advantages, consider a university's registration system. First, a HashMap is ideal for caching frequently accessed data, such as storing student data for quick retrieval in a web application. It's useful for counting occurrences, like the number of students registered for each class, where class codes are keys and student counts are values. HashMap is ideal for tasks like looking up a student's data by student ID. You store IDs as keys and student data objects as values, making lookups very fast. You can group data based on a specific attribute, like grouping students by grade. Now that you know these common use cases, let's explore when a HashMap is the best choice for your project. In general, a HashMap is great for a number of tasks and project conditions. HashMap is excellent for frequent lookups. First, if you frequently search for data by identifier, such as a student ID, HashMap is an excellent choice due to its fast lookup time. When data volume changes frequently and unpredictably, HashMap handles it well because it resizes as needed. And lastly, HashMap works best when keys are well distributed, meaning only a few keys hash to the same array index. This is difficult to predict, but complex keys are less likely to collide. While HashMap is fast, it comes with trade-offs. Most critically, it uses more memory than other collection types. A HashMap requires space for the underlying array and additional space to maintain efficiency as it grows. If memory usage is a concern, consider other data structures like ArrayList or LinkedList. When selecting a data structure, consider your application's needs and ask, how frequently will I need to search, insert, or delete data? Is minimizing memory usage a priority for this application? Do I need the data to be sorted or evenly distributed in memory? For example, choose a HashMap for speed, especially when you need fast searches by identifier and quick insert and delete operations. But consider a TreeMap, ArrayList, or LinkedList when sorting data or maintaining sequence, such as sorting students by last name. If conserving memory is important, a standard array, ArrayList, or LinkedList might be better. It is important to understand that a HashMap functions efficiently when the hash values of its keys are evenly distributed across its buckets. Larger and more complex keys tend to generate a wider range of hash values, which helps ensure a balanced distribution, reducing the chances of multiple keys being mapped to the same bucket, thus improving performance. A TreeMap is an option too for sorted data and keeps keys in order, but it is slower for basic operations. Java's HashMap is a powerful tool for efficiently storing and retrieving key value pairs. In this video, you've learned how HashMap works, how well it performs, and when it's best to use. In summary, HashMap is ideal for caching, counting frequencies, and quick lookups. However, be mindful of its high memory usage and the potential for slowdowns due to hash collisions. By selecting the right data structure, you can leverage HashMap for efficient, high-performance solutions while managing trade-offs effectively. Picture this. You're developing a university class registration system. One problem that needs to be addressed is the waiting lists for full classes. In this scenario, you have to maintain the order in which students were added to the waiting list, but you also need to be able to find students quickly, regardless of their position on the waiting list. While a HashMap is unordered, there is another Java class that you can use to achieve this, the LinkedHashMap. In this video, you will understand what a linked hash map is and how it's used, specifically how it can maintain the order of entries while providing efficient access to data. Remember that when you iterate through a hash map, the order in which you add the entries and the order they enumerate are unrelated. Hash maps do not order their entries. A linked hash map, on the other hand, maintains the order in which the entries were added. For example, in the registration system, a linked hash map can maintain the order in which students are added to the waiting list. To better understand how the linked hash map provides ordered entries, you can develop an application that adds students to a linked hash map. Then, print out the entries and see if the enumerated order matches the order in which they were added. The first thing you need to do is import the linked hash map type into our program. Like the hash map, the linked hash map is a member of the Java util package. Next, you create a class with a main method as a framework for our example. Once you have accomplished that, you can create the linked hash map. The linked hash map will store students' ID numbers as the keys and their full names as the values. You can add several students to the linked hash map in the order they requested to be added to the waitlist. You can iterate through the linked hash map to see all the students and the order in which they were added to the linked hash map. To do this, add a new static method below the main method that will print out the contents of the linked hash map. You will use this output method frequently. The variable I shows each student's numerical position on the waiting list. The for each loops through each entry in the linked hash map, casting them into the map entry type. It then prints the student's position, ID, and name. Call this method right after you add all the entries to the linked hash map. When you run the application, the output demonstrates that the enumerated items are in the same order as they were added to the linked hash map. The result is that the order in which the entries were added is preserved, with the first entry added being the first one printed. An interesting feature of the linked hash map is that it maintains the position of a key even if you update it with a different value. For example, use the put method to update the value associated with the fourth entry from John Smith to Lydia Apple, as shown here. When you print out the linked hash map, the order is the same, but the name associated with the fourth entry has been changed to Lydia Apple. This default ordering of entries in the linked hash map is called insertion order and is useful when you need to maintain the order in which items were added. The linked hash map supports another ordering system called access order, which will be covered in a future video. The TreeMap, similar to the linked hash map, can maintain the natural order of a key, meaning that it keeps whatever order might have built into the key. With the TreeMap, you can also customize the ordering. The TreeMap will also be covered in a future video. To wrap up, we've seen how the linked hash map can be a powerful tool in our university class registration system, especially for managing waiting lists. By maintaining the insertion order, linked hash map ensures that students are processed in the exact order they join the waitlist, while allowing quick access to any student's information. This balance of order and efficiency is crucial for developing a seamless and effective registration system and any other application that requires maintaining ordered entries with quick access. The fast access offered by HashMaps is invaluable for quick data retrieval. But what if they also kept entries in order? That would be useful for scenarios like processing tasks in the order they arrive, or maintaining the sequence of events, like a waiting list. In this video, you'll learn how to manage elements in a linked hash map, including adding, removing, and retrieving entries while preserving their insertion order. Unlike a hash map, where the order of entries is unpredictable, a linked hash map maintains the sequence in which items were added. This feature is crucial when order matters. But just like a hash map, the linked hash map supports essential methods like put, get, and remove. This gives developers efficient data handling with the added benefit of preserving entry order. Let's consider an example. In the waiting list scenario, put is used to add students to a waiting list, and get retrieves their details. The linked hash map also has special methods for retrieving the first and last entries. So, when a spot opens up on the waiting list, it's given to the first person on the list, identified using first entry. The output shows that the lucky student who made the first entry is John Wells. Similarly, last entry returns the last person added to the list. Once John Wells gets into the class, we can remove him from the waitlist using the remove method. The remove method then returns the value of the removed entry, confirming that the action was successful. Nice. Knowing who's first and last is just one possible action. But what about everyone else on the list? With a little code, you'll be able to see who's still on the waiting list. As you can see, John Wells has been removed from the waiting list. But now all the other names are visible too. The linked HashMap includes the putFirst and putLast methods, which allow you to place an entry at the beginning or end of the list. However, what may not be obvious is how these methods, along with put, affect existing key value pairs. If the key used in putFirst or putLast doesn't already exist, the entry is simply added to the first or last position. Similarly, if put is used with a new key, the entry is added at the end, just like with putLast. However, if putFirst, or putLast are used with an existing key, the location of that key value pair will change, depending on the method used. For example, if you take an existing entry and add it again with putFirst, it not only updates the value, but also moves that entry to the first position. You can try this with the ID CS9857859, which was originally assigned to John Smith. The output shows that David Bean has replaced John Smith for that student ID and is now at the top of the list. The behavior for putLast is similar to the behavior for putFirst, except the entry moves to the end of the list. The put method works a bit differently. If the key is already present, the value is updated, but the key's position remains unchanged. Let's try this with the key AB4453455, currently linked to David Winston in the third position. If we use put to assign Bob Schmidt to this key, it will update the value, but keep the key in the third position. Now Bob Schmidt has replaced David Winston, but the key remains in the third position. Perfect. In this video, you've seen how linked map combines fast access with order preservation, and how key methods like put, get, remove, putFirst, and putLast help you manage and maintain the sequence of your data efficiently. These basic yet crucial techniques equip you to handle complex data management tasks with confidence, ensuring your applications run smoothly and efficiently. Managing data efficiently is key, especially with large datasets. But what if you need to prioritize some key value pairs while discarding those used less often, like a university might in its registration system? In this video, you'll learn how to create an access order linked HashMap, where entries are ordered by how often they're accessed, not when they were added. To better discuss the concept of access order, consider a university's registration system. Imagine a class called Student that tracks key details for each student. As students log in, the application loads their information using this class. Having quick access to the student's ID, name, and language helps the system serve the student better when inputting data or reviewing information. It would drain computational resources to keep 40,000 student objects in memory. To manage this, you can implement a custom linked HashMap that maintains a limited number of student objects in memory. These objects are used throughout the registration process, accessed with the get method, and updated with the put method as students register and input data. As students log in, the custom linked HashMap stores their student objects. When it reaches its maximum capacity, it makes room for new logins by dropping student objects that haven't been used for a while. This might happen, for example, if students walk away from the registration process or close the app without logging off, which happens a lot more than you think. To save resources, we want to keep only the most active student objects in our custom linked HashMap. The rest can be stored in a database or on disk and retrieved as needed. This approach is known as the least recently used, or LRU, caching algorithm. In short, the linked HashMap automatically removes the least recently used objects to keep only the most active ones in memory. It's a common strategy to reduce system resource loads, and linked HashMap natively supports this algorithm. To use the LRU features of linked HashMap, you must extend it and override the remove eldest entry method. This method returns false by default, so the least recently used entries are not removed when new objects are added. You can modify this behavior by creating a custom class that extends LinkedHashMap. Notice that the AccessOrderMap class extends LinkedHashMap, adding a capacity variable, defining its constructor, and overriding the removeEldestEntry method. The AccessOrderMap constructor calls the LinkedHashMap superconstructor, passing in the capacity parameter while keeping a copy of the value. It also passes a standard load factor, the default setting for balancing memory and performance, and true for the access order parameter. The access order boolean tells the LinkedHashMap to move the most recently accessed student object to the last position, shifting all other student objects toward the first position. The overridden removeEldestEntry method checks the map's current size against its capacity. If the size exceeds the capacity, it returns true, removing the first entry. If not, it returns false and nothing is removed. So if you print the contents of AccessOrderMap after adding 4 student objects, you'll see their order matches the order in which they were added. As expected, Antonio Lopez was added last, so he is in the last position. John Wells, added first, is in the first position as the least recently used object. The order changes as soon as we do anything to the entries in the LinkedHashMap. For example, if you call get on the third entry like this, and then print out the contents again. David Winston, who was in the third position, is now in the last position because it was the most recently used object. If adding a new entry causes the LinkedHashMap to exceed its capacity, the least recently used object, which is in the first position, will be removed. To see this in action, write the following code to add a new student object and then print the LinkedHashMap again. The entry with an ID of 1, John Wells, in the first position was removed as planned, and the new entry with an ID of 5, Alan Cornworth, was added at the end. Perfect. The order has shifted. The LinkedHashMap now reflects the LRU caching algorithm. The most recently used objects are preserved at the end, while the least recently used are ready to be removed from the front. In this video, you've learned how an access order, LinkedHashMap, prioritizes the most frequently used entries while automatically discarding the least used ones. By extending the LinkedHashMap and overriding key methods, you can efficiently manage memory and performance, making this approach ideal for implementing caching mechanisms like LRU caches. Whether managing a registration system or large datasets, access order LinkedHashMap ensures crucial data is always accessible. This maximizes the efficiency and performance of any application you're working on. Imagine a bustling university registration day, where thousands of new and returning students sign up for classes. Your task is to keep all their names in perfect alphabetical order for each subject, no matter the chaos. But here's the challenge. Students register randomly, not alphabetically. So, you need a way to ensure every new registration fits into place alphabetically. Enter the TreeMap, your tool for turning chaos into order. A TreeMap works much like a LinkedHashMap, storing key value pairs. But unlike a LinkedHashMap, a TreeMap automatically sorts these pairs. Your keys will be sorted alphabetically from A to Z if they are student names. Conversely, they'll be sorted from 0 to 9 if the keys are numbers. In other words, string-type keys are ordered alphabetically, while numbers are stored in ascending numerical order, because these are the natural orders of these kinds of key types. Let's explore this in action. You'll create an application that registers students, keeping their names and home countries alphabetically. Start by importing the TreeMap and map types. The map type is needed to print out the entries in the TreeMap. Next, create a framework for the application with a class and main method for executing the code. Now you can create an instance of the TreeMap and add several students and their addresses. Finally, print out the entries in the order provided by the TreeMap, using a static method called printTree. Now, if you run this application, the output will show the students listed alphabetically. Remember that without specifying it, the TreeMap automatically ordered entries by their key, the name, in ascending alphabetical order. Had the keys been numerical, integers, doubles, etc., the items would have been ordered in numerical ascending order. The Java API defines several temporal types, such as date and time, that support natural ordering. However, most of the Java types you will use, besides strings, numerical values, and temporal types, do not support natural ordering. To account for this, use a pluggable ordering object called a comparator for types that do not have a natural order in Java, including those you define yourself. A comparator is any class that implements the Java util comparator interface. This interface has more than 24 methods, but the compare method is what you will focus on now. To demonstrate, here is an implementation of the comparator interface that orders the students by their last names in ascending alphabetical order. The compare method takes two objects that should be compared and returns an integer, which can be a negative number, a 0, or a positive number. If the integer returned by the compare method is negative, the first parameter is less than the second object. For example, 1 is numerically less than 2, and B is alphabetically less than A. If the compare method returns 0, the two objects are somehow equal, 1 equals 1 and A equals A. If it returns a positive number, the first object is, somehow, greater than the second. For example, 3.2 is numerically greater than 3.0, and the word cat is alphabetically greater than bat. The last name comparator compares two objects by their last names. First, it casts the objects passed into the compare method to string types. Then it sends each string to a custom method called lastName. The lastName method simply looks for the last space in the string and returns everything that follows. The underlying assumption is that the space separates the first name from the last name, and everything that follows that space is the last name. It's not perfect, but it works for this example and demonstrates that you can customize your processing when implementing the comparator interface. After the lastName method returns, you can use the lastName string values and the string type's built-in natural ordering to determine whether the last name of the first key is less than, equal to, or greater than the second key. The compare_to method is built into the string type and does the same action as a comparator. It returns a negative number if the calling string appears alphabetically before the parameter string. It returns 0 if both strings are the same. It returns a positive number if the parameter string comes before the calling string alphabetically. Let's test this comparator in action. Create a new instance of the TreeMap, but this time pass in the lastName comparator in the constructor. Next, add all the key value pairs in the same order you did for the first TreeMap. When the second TreeMap is enumerated and printed, the entries are printed alphabetically by last name, not in the natural order of the full name or the order in which they were added. Overall, the TreeMap provides tremendous advantages when ordering key value pairs, and you can take advantage of custom ordering by creating comparator objects. The TreeMap isn't just about keeping things in order, it's about putting you in control. You can tailor the sorting to your needs with the right compare method. Experiment with your comparator objects and see how custom ordering can simplify your coding challenges. Imagine effortlessly transforming messy data into neatly ordered structures. Take the plunge, start experimenting, and unlock the full potential of TreeMap. Picture yourself designing a reporting feature for a university's registration office. This tool must provide swift and precise access to student data. How would you ensure that the GPA scores are managed efficiently and accurately? TreeMaps can be an ideal solution for such challenges that involve sorting and retrieving data based on keys. In this lesson, you will learn how to effectively navigate through the elements of a TreeMap, using methods like first key, last key, higher key, and lower key. First, a TreeMap stores key value pairs in a sorted order. This sorting is based on the key's natural ordering, or by a comparator provided at TreeMap creation time. The inherent ordering allows for efficient retrieval of elements based on their keys. To understand how this is useful in the real world, imagine you are creating a TreeMap that uses students' GPAs as keys and their names as values. For simplicity, assume no two students have the same GPA. The TreeMap does not have a comparator, so it will use the natural ordering of the keys, which in this case are double types. When you run the program, the output prints the students from the lowest GPA to the highest. Great. And the TreeMap automatically orders the key value pairs according to the natural ordering of the double type used as the key. Now imagine you just need to know which student has the lowest GPA. The first key method returns the first, in other words the lowest, key currently in the map. Because of natural ordering, this would also be the lowest GPA. Here, the first key method is used to access this lowest key value. The next line uses the get method to retrieve the value associated with that key, in this case, the student's name. The last two lines print out the results. If you know the types of the keys and the values, you can cast them to their proper types as you access them in the TreeMap. When the types of keys or values are not known or incorrectly cast in a TreeMap, it can limit how the map is used and may lead to runtime errors. Casting the types is not needed in this scenario, but it would be helpful in cases where you need to work more intensely with the keys and values rather than just printing them out. Another way to fetch the first key value pair is using the first entry method. This makes the code look more complicated because you have to deal with the map entry type, but it's also more convenient. The output is the same. We just use first entry instead of first key. Note that all methods here have a map entry counterpart for fetching both key and value. We'll use key methods, but map entry methods are also available. Now let's turn to another useful method, the last key method, which accesses the key with the highest value in the TreeMap. In terms of GPA scores, this method would access the highest GPA according to the natural ordering of the double values. Calling this method is straightforward. Using object allows the variable to hold any type of object, providing flexibility but requiring type checking and casting if you need to use the value in a type-specific way. The output includes the student with the highest GPA was successfully retrieved from the TreeMap. Perfect. To get more specific with our navigation, the higher key method returns the next higher key compared to the key passed in as a parameter. To do this, call the method using one of the existing keys and print the output. Notice that higher key method fetches the next higher key, 3.75, not just any higher key. The higher key method works with any parameter, not just existing keys, as long as the parameter is the same type as the keys in the TreeMap. For example, here we are searching for the next higher GPA above 3.6. In the output, the 3.6 GPA isn't an existing key in the TreeMap, but the higher key method used it to find a GPA that was the next higher GPA. Just as the higher key method finds the next higher key compared to the parameter, the lower key method finds the next lower key in the TreeMap compared to the parameter. If no higher key or lower key exists, the method returns null. This can be used with any parameter of the right type, not just existing keys. When you run the program, the result reveals that 3.5 is the next lower key below 3.6. There are other lower keys in the TreeMap, such as 3.25 and 3.0, but the next lower key is 3.5. Navigating a TreeMap is an essential skill for Java developers. The TreeMap class provides methods to efficiently traverse and manipulate elements based on their keys. Understanding methods like first key, last key, higher key, and lower key allows developers to leverage the TreeMap's sorted nature for efficient key-based operations. Skills for effectively managing and navigating datasets are valuable for solving real-world challenges, such as developing dynamic reporting features for university registration systems or any application requiring efficient data organization and retrieval. By mastering these methods, you'll ensure your Java applications and solutions are both performant and robust. Java developers use a variety of data structures, each offering unique performance characteristics and specific use cases. Among the most useful advanced data structures in Java, the TreeMap class stands out for its ability to maintain key value pairs in sorted order. In this lesson, you'll explore TreeMap's performance, learn how to handle common use cases, and discover when it's best to use TreeMap over other data structures, specifically HashMaps. So, how exactly does a TreeMap organize its data so well? A TreeMap uses what's called a red-black tree approach to organize entries internally. In a TreeMap, each key value pair links to two other entries, one with a lower key and one with a higher key. This structure ensures the keys are maintained in sorted order, which is great for efficient data retrieval and maintaining sorted sequences. In the tree, the root is the entry with the key of 10. Keys lower in order are referenced on the left, and the higher keys are on the right. So, for example, 5 is found to the left of 10 because it's a lower value, and 15 is to the right because it's higher. When the entry with the 3 key is added, it's less than 10 and less than 5, so it falls to the left reference of the entry with the 5 key, and so on. This structure is great for ordering any set of keys naturally or by comparator. The TreeMap continuously works to keep the structure balanced, much like a well-architected pyramid. It aims to minimize the width and height of the tree, ensuring efficient data retrieval and maintaining sorted sequences. This maintenance impacts performance, as the operations of adding, removing, and finding elements all have a time complexity of O log n, where n is the number of elements in the TreeMap. This is because the TreeMap doesn't use an underlying array, like a HashMap. Instead, it links all its entries together in a pyramid structure. This results in more complexity, and more time is required to find, add, and remove key value pairs than with the HashMap. Another key performance characteristic of a TreeMap relates to iteration. Iterating over the key or values is relatively fast with a TreeMap because the keys are maintained in sorted order. The TreeMap maintains extra data. Each entry links to 2 other entries to ensure the tree remains balanced in a pyramidal shape. This ordered structure facilitates efficient retrieval and is particularly useful for applications requiring ordered data processing, such as range queries and data navigation. However, note that while this memory overhead is generally not significant, it can be a consideration in memory-constrained environments. In terms of use cases for a TreeMap, 2 stand out: sort ordering and navigation. When the requirement is to maintain elements in a sorted order, TreeMap is the go-to choice. For example, an alphabetical list of students. The TreeMap also provides methods that make it easier to navigate among keys, including the methods first key, last key, lower key, and higher key. For example, finding the lowest or highest GPA among students at a university. TreeMap and HashMap are suited to different use cases, each offering unique advantages. Let's highlight the key differences to help you make informed decisions on which to use and when. First, the HashMap is faster than a TreeMap because it uses an array internally and indexes entries according to the hashcode of their keys. A TreeMap, on the other hand, links entries together, requiring more work and time to add, remove, and find entries. The HashMap also uses less memory than a TreeMap because it maintains fewer objects than a TreeMap. While the differences are negligible with small datasets, they become more important with very large datasets. Crucially, the HashMap does not maintain entries in any particular order. When you iterate through a HashMap, you cannot predict in what order the key value pairs will be enumerated. A TreeMap maintains the natural order of the keys, or it can be initialized with a comparator to maintain a custom order. Finally, the navigation capabilities of a TreeMap are more sophisticated than a HashMap. Both the HashMap and TreeMap can fetch a value directly by its key and iterate through the entries, but the TreeMap can also access entries based on their relative sort order, such as the next highest key, something that the HashMap cannot do. To wrap up, the TreeMap in Java is a powerful data structure that offers efficient sorted key value pair management. Its performance characteristics in adding, removing, and finding key value pairs make it suitable for various use cases where order and consistency are paramount. A TreeMap does have trade-offs in terms of memory usage and slightly slower operations compared to HashMap. However, its ability to maintain order and provide more sophisticated navigation makes it indispensable in scenarios requiring sorted data. In short, choosing between TreeMap and HashMap ultimately depends on your application's specific requirements. For sorted data, TreeMap is the better choice. For fast access and lower memory usage, HashMap is preferable. By understanding these differences, Java developers can make better informed decisions about when to use advanced data structures. This ensures their applications perform optimally and meet the requirements for order and efficiency. Imagine you're using your favorite text editor and just made a mistake. You instinctively press Ctrl-Z and the error disappears as if it never happened. But have you ever wondered how that undo action works? Do you know what's happening behind the scenes when you correct your mistake with a single keystroke? By the end of this video, you'll understand the practical applications of stacks. And having studied the complete lesson, you'll understand how stacks are used in 3 key areas: managing function calls in programming, converting expressions from infix to postfix, and implementing undo mechanisms in software. In Java, a stack is more than just a concept. It's a data structure implemented with its own dedicated class called stack. This means that when you create a stack in your Java program, you're essentially creating an object of this stack class. This stack object comes equipped with a set of methods specifically designed to manipulate data. At their core, stacks operate on this last in, first out, or LIFO principle. To understand LIFO, imagine a stack of plates at a buffet. When you stock up the plates, you add a new plate on top of the stack of plates. If you need to use a plate, you remove the top plate first. The plate at the bottom stays there until all the plates above it are removed. Stacks work precisely like that. You push data onto the stack, and when you need to retrieve it, you pop the most recent data off first. This behavior makes stacks incredibly useful in scenarios where you must keep track of actions or tasks in a specific order and revisit them in reverse. But how does this abstract concept of stacks translate into something practical in the programming world? Let's explore one of the most fundamental areas where stacks play a critical role in function calls. Have you ever wondered how a computer knows where to return after calling a function? Here's where stacks come into play. When a function is called, the code's current position and local variables are pushed onto the stack. The function then executes, and once it's done, the program pops the return address off the stack and jumps back to where it left off. This process ensures that the program can handle multiple nested function calls and return to the correct point in the code each time. Without stacks, keeping track of these return points would be chaotic and error-prone. The initial call is add 3 and 2. The stack starts with add 3 and 2 as the top and only element. The first recursive call is add 4 and 1. Therefore, add 4 and 1 is now pushed onto the stack, becoming the new top element. Add 3 and 2 remains just below it. The second recursive call is add 5 and 0. Add 5 and 0 is pushed onto the stack, becoming the new top element. The previous top, add 4 and 1, is now just below it. Returning from recursive calls, as add 5 and 0 hits the base case y equals 0, it returns a value, and the stack begins to unwind. Add 5 and 0 is popped off, making add 4 and 1 the top element again, followed by add 3 and 2 as the stack continues to unwind. Next, let's talk about expression evaluation, particularly converting infix expressions. For instance, 3 plus 4 multiplied by 5 to a postfix notation like 3, 4, 5 multiplied sign, addition, sign. This might sound complex, but it's a critical process in how computers evaluate mathematical expressions. In infix notation, operators are placed between operands, which can lead to ambiguity in the order of operations. To simplify this for computation, the expression is converted to postfix notation, where the operators follow the operands. Stacks are the perfect tool for this conversion because they allow us to temporarily store operators and ensure they are applied in the correct order. By pushing and popping operators at the right moments, the stack helps us rearrange the expression into a form that's easy for computers to evaluate. Starting with the infix expression, 3 plus 4 multiplied by 5, where operators are placed between operands. Operator precedence can complicate the evaluation, so converting to postfix notation simplifies it. Now, let's take a look at this conversion, step by step. First, the operand 3 is encountered and goes directly into postfix expression. Next, the plus operator appears. Since the stack is empty, plus is pushed onto the stack. The next operand 4 is added directly to the postfix expression. Now, the multiply operator is encountered. With higher precedence than plus, multiply is pushed onto the stack above plus. The final operand, 5, is then added to the postfix expression. With no more operands left, the stack proves its usefulness. Operators are popped in the correct order. First, multiply, then plus, ensuring the postfix expression is properly formed. The final postfix notation is 3, 4, 5 multiply plus. Thanks to the stack, the operations are organized in the correct sequence without needing to consider precedence directly. That's how the stack makes converting infix to postfix easy. It uses its LIFO order to automatically figure out the right order for math operations. Finally, let's understand stacks through the undo mechanism mentioned earlier. Whether in a video game, text editor, or other software, the ability to undo actions relies heavily on stacks. Every time you act, the software pushes a record of that action onto a stack. If you decide to undo the action, the software simply pops the most recent action off the stack and reverses it. Stacks are ideal for managing a history of actions because of their LIFO nature, allowing you to backtrack step by step. Actions are added to the stack from the bottom up, with each new action placed on top. During an undo, actions are removed from the top down in reverse order. Stacks are everywhere, from the books in the library to the software we use daily. By understanding how they work and recognizing their use cases, you can see the power of this simple yet effective data structure. Whether you're managing tasks, navigating through web pages, or coding, stacks provide an organized way to handle data and operations efficiently. Embrace this concept, and you'll find yourself better equipped to tackle various challenges in both programming and everyday life. Imagine this. You're in your kitchen, stacking clean plates after washing them. Naturally, you place one plate on the other, making a neat stack. And when it's time to grab a plate, you don't reach for the bottom one. You pick the one on top, right? Well, that's exactly how a stack works. In this video, you'll explore the concept of stacks, one of the most important data structures in programming. By the end, you'll know what a stack is, how it operates, and how to use its basic functions. So what exactly is a stack? It's a data structure that works on the last in, first out, or LIFO principle. You've already seen this in action with your plate stack. The last plate you put on the top is the first one you take off. Stacks in programming work precisely like that. But before we go deeper, let's quickly define a linear data structure. This type of data structure has elements arranged in sequential order. Think of it like a line of people waiting to get into a concert. Each person stands in a specific order, one after another. Stacks aren't just a theory, however. They're used all over in programming. For example, when your browser lets you click back to return to the last page you visited, it's using a stack. Or when you're undoing a mistake in a document, same thing. Understanding stacks can help you recognize these patterns in everyday coding. Now let's get into the main operations that make a stack tick. There's push, pop, peek, and isEmpty. They sound simple, but they're also super important for managing data in a stack. Let's break them down. First up is the push operation. This is when you add an item to the top of the stack. Picture adding a plate to your stack of plates. It goes right on top, becoming the new top of the stack. In coding, when you push an item, it becomes the top item in the stack. To see how this works, imagine your stack of plates. Picture an empty stack where you first place plate 1. Then, plate 2 goes on top of plate 1. Finally, you'll add plate 3 on top of them all. As you'll see shortly, the last plate you added, plate 3, will be the first removed in a pop operation. This is how stacks follow the last in, first out principle. Now, what if you need an item? Then you pop it off the stack. The pop operation removes the top item from the stack. Just like grabbing the top plate, the last item you added is the first one to go. This operation usually gives you the removed item as well, so you can use it in your code. Let's return to the stack of plates. You have 3 plates in your stack, plate 3, plate 2, and plate 1. When you pop, plate 3 is removed first, followed by plate 2, and finally plate 1. Now the stack is empty. What if you don't want to remove the top item, but just want to see what's there? That's where the peek or top operation comes in. It lets you take a quick look at the top item without popping it off the stack. It's like glancing at the top plate to check if it's the right one. Let's return to the plates. If you peek when there's only one plate, you'll see plate 1. Now, if you push plate 2 on top and peek, you'll see plate 2. Finally, if you push plate 3, a peek will show that plate 3 is now on top. So with the peek operation, you get to see the top item without making any changes to the stack. In a stack data structure, peeking is useful when you need to know the top or most recent element, but want to keep the stack unchanged. Finally, there's the isEmpty operation. This one's handy when you need to check for any items left in your stack. When you run this operation and the stack is empty, it returns true. If not, it's false. Simple, right? It helps avoid errors, especially when you try to pop or peek at an empty stack. For example, in your plate scenario, you start with an empty stack. After pushing plate 1, the stack is no longer empty. The more plates you push, the more items the stack has. But before that first push, is empty would return true, meaning the stack has no elements yet. So, that's a stack in a nutshell. Just remember the last thing in is the first thing out. Elements are pushed onto the top of the stack and popped off from the top, just like how you'd handle a stack of plates. Remember this and you've got the essence of stacks. Keep practicing these concepts because they're foundational in programming, and you'll see them pop up, pun intended, in more advanced topics down the line. Imagine you're developing a web browser's history feature, where each new page visited gets added to the top of the history list. To manage this effectively, you're considering using a stack. But how do you choose the right implementation for your stack using arrays or linked lists? Each choice impacts how efficiently the browsing history can be managed, especially regarding time and memory usage for different types of users, from casual browsers to power users visiting hundreds of pages. In this video, you'll explore the time complexity of stack operations in an array-based implementation. You'll also compare linked list-based and array-based stack implementations, focusing on their flexibility and memory usage. Finally, you'll gain an understanding of the trade-offs involved in choosing between these two common implementations. Let's get started. Stacks can be implemented using arrays or linked lists. Both implementations adhere to the last in, first out, or LIFO principle, but they differ significantly in handling tasks like pushing, popping, and peeking. It's important to understand these differences when choosing which method to use in different situations. Let's start with the array-based implementation. In this approach, a stack is implemented using a fixed-sized array. Here's a breakdown of the key operations. Imagine your stack as a row of boxes. It currently holds 3 items, 20, 40, and 60, with 60 on top. When you push 80 onto the stack, it gets added to the next empty spot, which is at index 3. Now, 80 is the new top item, sitting on top of the stack. If you just want to check what's on top without changing anything, you peek. Right now, peeking shows 80, the top item. It's like looking inside the top box without taking it out. When you pop the stack, you remove the top item, 80. After popping, 60 becomes the top item again, and the space where 80 was is now empty. Let's examine the pros and cons. Array-based stacks are straightforward and offer fast access to elements. The main limitation is the fixed size. Array-based stacks use the same sizing rules that you learned when working with arrays in Lesson 1. If the stack exceeds the array's initial size, resizing is required, which is costly in terms of time. Now let's consider the linked list-based implementation. In this approach, each element in the stack is a node in a linked list, with each node pointing to the next one. In this diagram, you'll notice the nodes are connected like a chain forming a stack. Node 1 points to node 2, node 2 points to node 3, and so on until the last node, node 4, which doesn't point to anything. When you push a new item onto the stack, a new node is created and linked to the current top. This new node becomes the top of the stack. If you pop the stack, the top node is removed and the next node in line becomes the new top. Peeking lets you see the top item without removing it. In this setup, peeking would show what's stored in node 4. Let's examine the pros and cons. Linked list-based stacks are dynamic and do not require a fixed size, making them more flexible regarding memory usage. The trade-off is that they require more memory per element due to the overhead of storing pointers, and they might incur additional overhead in terms of cache efficiency. Next, let's compare both stack implementations regarding flexibility and memory usage, starting with array-based stacks. Imagine you know exactly how many elements your stack will hold. In this case, an array-based stack might seem like a great choice. An array-based stack is simple, but limited to max size elements. If you exceed this, the stack needs to resize, which involves creating a new array and copying elements over, turning an order of 1 push operation into an order of n. The stack pre-allocates a fixed block of memory. If the stack doesn't fully use it, memory is wasted. Reallocating more space is costly in both time and resources. Push, pop, and peek are generally order of 1, but when the array is full and needs resizing, push becomes order of n, due to the time required to copy elements to a new array. Now, what if the number of elements in your stack is unpredictable? This is where a linked list-based stack shines. There's no predefined size limit. You can keep adding nodes as needed, and the stack will grow dynamically. This makes push operations consistently order of 1, regardless of the number of elements. Each node requires additional memory to store a reference or pointer to the next node. While this adds flexibility, it also increases the memory footprint compared to arrays, especially for large stacks. However, for very large elements, the overhead of pointers might become negligible. Push, pop, and peek operations are consistently order of 1 because they only involve updating or accessing pointers with no need for resizing. Array-based stacks are best when you know the stack's maximum size in advance and want to minimize memory overhead. However, resizing can be a costly order of n operation. On the other hand, linked list-based stacks are ideal for scenarios where the stack size is unpredictable. They offer great flexibility with consistent order of 1 time complexity for push, pop, and peek, but at the cost of extra memory for pointers and potentially lower cache efficiency. In this video, you learned that choosing between an array-based and a linked list-based stack depends on the specific requirements of your task management scenario. Consider the nature of the tasks you're managing when deciding on a stack implementation. Understanding the time complexity and memory trade-offs will help you make the best choice for your application. Imagine you're standing in line at a coffee shop. Everyone waits their turn, and the first person in line is served first. This simple concept of first come, first served is how a queue works. But did you know this everyday scenario is also crucial in how computers manage tasks? In this video, you'll explore the practical applications of queues, a fundamental data structure in computer science. You'll gain an understanding of how queues play a vital role in operating systems for CPU scheduling, handling I/O requests, and managing tasks like printer spooling. Finally, you'll delve into how queues are used in networking to manage data packets efficiently. Let's examine queues in more detail to learn more. A queue is a linear data structure that follows the first in, first out, or FIFO principle, similar to the line at the coffee shop. The first element added to the queue is the first one to be removed. This orderly approach is perfect for managing tasks where timing and sequence are critical. In contrast to stacks, which follow the last in, first out, or LIFO principle, queues ensure that elements are processed in the order they arrive. Like the coffee shop line, the first person to arrive is the first person served. Queues are used in various areas of computing to manage tasks efficiently and ensure that processes are handled in a fair and organized manner. Let's examine how the queue works in this coffee shop scenario. Here, person 1 is at the front of the line, so they're served first, as shown by the red arrow labeled 1. Once they're served, they leave the queue. Next, person 2 steps up, indicated by the yellow arrow labeled 2. They are served and then leave the queue. This process continues with person 3 and 4, following the arrows labeled 3 and 4. Each person is served in the exact order they arrived. This simple example of a queue demonstrates how tasks are managed efficiently and fairly. Now let's explore how this concept of queues applies to more complex systems, like operating systems, where they are essential for keeping everything running smoothly. Think of an operating system as the manager of a bustling office. It has to handle multiple tasks, prioritize them, and ensure everything is done in the right order. Here's where queues come into play. The CPU is like the barista in the coffee shop, taking one task at a time and completing it before moving on to the next. But in a computer, there are countless tasks waiting to be processed. A queue helps manage these tasks by organizing them in the order they arrive. For example, in a first-come, first-served, or FCFS scheduling, the CPU processes tasks in the exact order they enter the queue, just like the first customer in line gets their coffee first. While this is similar to the FIFO principle we discussed earlier, FCFS is a specific scheduling algorithm that applies the FIFO concept to CPU task management. Here, tasks line up in a queue, task 3, task 2, and task 1. The CPU processes them in the order they requested, following the FCFS method. Task 1 goes first, followed by task 2, and then task 3. This is known as first in, first out, or FIFO, just like customers in line at a coffee shop. Devices like keyboards, mice, and printers constantly send requests to the CPU. These requests are placed in a queue, ensuring each request is handled in turn. This prevents chaos and ensures no request is lost or ignored, like how everyone in the coffee shop line eventually gets their order. Here we have 3 devices, a keyboard, a mouse, and a printer. Each of these devices sends requests to the CPU. These requests are represented by the boxes labelled Request 1, Request 2, and Request 3. These requests don't go directly to the CPU. Instead, they are placed in a queue, which organises them in the order they arrive. Notice how Request 1, Request 2, and Request 3 are lined up in the queue. The CPU processes these requests one by one, starting with the first in line, Request 1, and then moving on to Request 2 and Request 3. Imagine several people in an office sending documents to a single printer, one after another. Instead of printing everything at the same time, which would be impossible, the printer uses a queue to manage the print jobs. The documents are printed in the order they were sent, ensuring the output is organised and predictable. This management of print jobs is known as spooling, and it's a perfect example of how queues help manage resources efficiently. Here, 3 people, person 1, person 2, and person 3, each sent a document to be printed. The documents are labelled Document 1, Document 2, and Document 3. Instead of being printed simultaneously, the documents are placed in a queue. Notice the order. The numbers 1, 2, and 3 indicate the sequence in which these documents entered the queue. The printer processes these documents, one at a time, following the received order. Document 1 is printed first, followed by Document 2, and finally Document 3. Queues aren't just useful in operating systems. They also play a crucial role in networking. When data is sent over a network, it's broken down into smaller units called packets. These packets need to be managed carefully to ensure that they reach their destination in the correct order and without loss. Here's how queues come into play. In a network, data packets from different sources arrive at routers and switches, which direct them to their destinations. These devices use queues to manage the incoming packets, ensuring they are processed in the order they arrive. This orderly processing prevents network congestion and ensures data is transmitted efficiently and reliably. In more complex networks, some data packets might need to be prioritized over others. For example, a video call might need to be prioritized over a file download to maintain smooth communication. Queues can be used to manage these priorities, ensuring that the most critical data is handled first while less urgent tasks wait their turn. In this video, you learned that queues are everywhere in computing, quietly ensuring that processes are managed smoothly and efficiently. Whether the CPU schedules tasks, handles input-output requests, manages print jobs, or transmits data over a network, queues ensure that everything is done in an orderly fashion. Just like in a busy coffee shop, queues help keep things fair, organised, and running smoothly, ensuring every task gets its turn. Imagine you're driving in the city during rush hour. You stop at a traffic signal and, to your dismay, see many cars ahead. The light changes and the car at the front goes first, followed by each car in order. This sequence of movement is like a queue data structure in Java. In this video, you'll get an idea of what a queue data structure is, specifically a standard queue. You'll see a breakdown of how a queue works using the first in, first out, or FIFO rule, and compare it to a real-world example to help you understand. So, what is a queue exactly? A queue is a linear data structure that stores elements in an ordered sequence. Elements are added at the back and removed from the front. A queue follows a first-in, first-out principle that defines its operation, making it ideal for scheduling processes or handling asynchronous data. To visualize the FIFO principle, think about how cars line up at the signal. The first car to arrive is the first one to leave. In the same way, the first element added to a queue is the first to be removed. A queue supports 2 primary operations, enqueue and dequeue. Let's quickly look at each. In a queue, you use the enqueue operation to add an element at the end, like a car joining the back of the line. DQ removes the first element from the front, just like the car at the front of the signal drives away when the light turns green. In a queue data structure, the first element added, or enqueued, is the first one removed, or dequeued. Let's see this visually. Imagine a queue of numbers starting with 2 at the front and ending with 6 at the rear. To dequeue, you would remove the front element, which in this case is 2. 3 now moves to the front of the queue. To enqueue, you would add a new element, 8, to the rear of the queue. You may have noticed the terms front reference and rear reference in the image. These play important roles. The front reference indicates the position of the first element in line. In other words, the next car to leave the traffic. This indicates the element that will be dequeued, removed, next. The rear reference represents the position where the next element joins. In other words, where a car joins the traffic line at the back. In the queue, this is where the next element will be enqueued or added. The front and rear positions change as more cars enter or exit the traffic line. Similarly, when elements are added or removed from a queue, the front and rear references adjust to show their new positions. Keep in mind that a queue can't accept more elements once it reaches its defined capacity. This constraint depends on the queue's implementation, whether it's backed by a fixed-sized array or a dynamically expanding structure, like a linked list. Now let's see how this works in Java. Let's first focus on the enqueue operation. When a new car arrives at a traffic signal, it joins the back of the line, just like the enqueue operation, where new elements are added at the rear and processed in order of arrival. In the code, the first step is to check if the queue is full using isFull. If it is, the process stops, and a message is displayed. Queue is full, cannot enqueue, in this case. If the queue isn't full, the rear index is incremented, and the new item is added to this updated rear position. Finally, the queue size is increased by 1 to reflect the new addition. Simple and efficient. Now let's focus on the dequeue operation. Here, the first element is removed from the front, like the first car to leave when the light is green. This process is critical because it keeps things running smoothly. Without removing the first car, no one else can move forward. If the car at the front stayed put, blocking everyone behind it, traffic would become chaotic. So, when the traffic signal light turns green, the car at the front of the line moves first, making room for the cars behind it to move up. This is how the dequeue operation works in a queue. The element at the front of the queue is the first one to be removed. In the code, first check if the queue is empty using isEmpty. If the queue is empty, a message is printed and -1 is returned. If not, the item at the front of the queue is stored and the front index is incremented to reflect the removal. The size is reduced by 1 and the dequeued item is returned. Great. Now you know how to use the enqueue and dequeue operations in your IDE. Now imagine you're in a long line of cars at a traffic signal, wondering how long the wait will be. You might peek ahead to see which car is at the front, but without moving or changing their positions, just a quick check to estimate when the light might change for you. In Java, you can use the peek operation to do something similar. Check the first element without altering the queue. This operation is useful in task scheduling to check the next task or data without modifying the queue or disrupting future operations. The code first checks if the queue is empty using isEmpty. If it is, it prints a message and returns -1 to show that there's nothing to peek at. If the queue isn't empty, it simply returns the item at the front without removing it or modifying the queue. Handy. In this video, you explored the concept of a queue as a linear data structure that follows the first in, first out principle. You observed how it can be compared to cars at the traffic signal, where the first car to arrive is the first to leave, and new cars join at the back of the line. Just like managing traffic flow, queues play a crucial role in many real-world scenarios, from task scheduling to resource management and computing. Keep practicing, and you'll see how valuable queues can be in solving problems. Searching for a friend's phone number in an extensive phone book can be done in 2 ways. You could start from the beginning and scan each name one by one until you find it. While this approach works, it could be time-consuming if your friend's name, such as Sarah, was listed towards the end. A faster way is to skip ahead to the section with names starting with S. This simple analogy reflects how search engines efficiently help to find information in the digital world. Searching algorithms are computing techniques for finding specific data within a larger data set. Searching algorithms are essential in today's digital world, where vast amounts of data are generated every day through activities like sending emails, posting on social media, and using cloud services. Finding a single file amid the sea of information, like locating one file on your computer without the search function, would be overwhelmingly time-consuming without efficient searching algorithms. Searching algorithms optimize this process by quickly and accurately identifying the required information, saving time and computer resources, such as storage, processing power, and memory. Several types of searching algorithms exist, such as linear search, binary search, jump search, exponential search, and interpolation search. Among these, linear and binary search stand out due to their simplicity and widespread use. In this video, you will learn about these two crucial searching algorithms. Let's get started. The linear search is the simplest type of searching algorithm. It's like starting at the beginning of the phone book and checking each name one by one until you find Sarah. In a linear search, the computer processes the data from beginning to end, comparing each item to the target item. For example, if you were searching for a number in a list of unsorted phone numbers, the linear search would start at the first number, compare it to your target, and move on to the next one if it's not a match. This process repeats until the number is found or the list ends. Linear search works best when dealing with small, unsorted data sets, or when data is arranged in a sequence that doesn't follow any order. It's often used when the data set is so small that sorting it or using complex algorithms isn't worth the overhead. It's also ideal when searching for specific items in a list, where the position of the item isn't known, like finding a name in an unordered contact list. Some of its advantages include being easy to implement and understand, working on any data structure, whether sorted or unsorted, and not requiring pre-processing or sorting, making it suitable for immediate searches. Its disadvantages include being slow on large datasets because it checks every element individually, and being inefficient with the time complexity of O of n, meaning the search time grows linearly with data size. In contrast, binary search is much faster, but requires sorting the data. Using the phone book analogy, it's like flipping directly to the section with names starting with S. Instead of checking each name one by one, you start in the middle of the book, roughly at the midpoint of the book based on the first alphabet of the name, and determine whether the name you're searching for comes before or after that midpoint. This way, you can eliminate half of the remaining names and focus on the relevant section. If Sarah's name is after the midpoint, you can immediately rule out the first half of the book from your search. You then repeat this process with the remaining half, selecting a new midpoint and deciding which half to search next. This method significantly reduces the number of comparisons needed to find the target by halving the search space at each step. The binary search is designed for sorted datasets. It's efficient in scenarios where data is already ordered or can be pre-sorted, like finding a word in a dictionary or looking up a number in a phone book. It's commonly used in algorithms where speed and large datasets are critical. A binary search is much faster than a linear search. While a linear search looks at every element one by one, a binary search has a time complexity of O, of log n, which means it repeatedly divides the dataset in half, narrowing down the search quickly. When used on sorted data, a binary search can narrow the target data in just a few steps, no matter how big the dataset is. However, there are some limitations to consider. First, the data must be sorted beforehand. If it isn't already sorted, that adds an extra step, slowing things down. Second, binary search only works with datasets that allow direct access, like arrays. It can't be used on unsorted or dynamically linked data structures. Understanding the fundamentals of searching algorithms, such as linear and binary search, can provide valuable insights into how computers operate behind the scenes to extract information quickly and efficiently. While linear search works well for small or unsorted data, binary search is the go-to strategy for efficiently handling large, sorted datasets. So, the next time you search for something on your computer or online, remember a well-designed algorithm is working behind the scenes to help you find exactly what you need as quickly as possible. Imagine this. You're at a garage sale with a table full of books, toys, clothes, and other goods. You're looking for a specific book to read. However, the objects on the table are not arranged in a particular order. How would you go about finding the book? The most basic technique is to begin at one end of the table and review each item individually until you discover the book you're looking for. This strategy, albeit simple, is precisely how a linear search works. A linear search is one of the most fundamental techniques for finding an item in a list or collection of data. The term linear refers to the fact that the search process proceeds in a straight line from the beginning to the end of the list. This approach doesn't require the list to be sorted and works with any type of data, such as numbers, words, and even objects. Let's break down the linear search algorithm step by step. First, The search starts at the beginning of the list. Then, the algorithm compares the current item in the list to the target value, the item you're searching for. If the current item matches the target value, the search is complete and the position of the item is returned. If the current item does not match the target value, the search moves on to the next item in the list. The process is repeated, comparing each item with the target value. Finally, if the search reaches the end of the list without finding the target value, it concludes that the item doesn't exist in the list. Let's demonstrate linear search using a Java example. You'll define an unsorted integer array of 6 numbers, specifically 3, 8, 1, 5, 9, and 2. The target number is 5. You'll write a class called linear search number example with the linear search method. This method takes an integer array and a target value to search for the target's index in the array. The target integer is searched inside the array and its index is returned. The linear search method is responsible for finding a target number in an array. The integer array represents the array of numbers you want to search, while the target integer is the number you are trying to find in the array. The for loop goes through each element in the array ARR. At each step, it checks if the current number, ARRI, equals the target number. If it finds the target, it immediately returns the index I, where the target is located in the array. If the loop finishes and the target isn't found, the method returns -1 to indicate that the number isn't in the array. Now back to the main method with an integer array of numbers and the target value. These two variables will be passed as arguments to the linear search method. Inside the method, define the unsorted array of numbers. The array numbers hold 6 different numbers. They are not in any particular order. Next, you define the target number that you want to search for. In this case, you're searching for the number 5 in the array. Then the program calls the linear search method to search for the target. This method returns the index of the target if it finds the number, or -1 if the number is not found. After the search, the result is stored in the variable result, and the program checks whether the target was found. If the result is -1, the program prints number not found. If the result is any other number, it prints the message number found at index, followed by the index where the target number was located in the array. Behind the scenes, the linear search algorithm would start by comparing 3 to 5. Since 3 is not equal to 5, it would move to the following number. Then, it compares 8 with 5. Again, they don't match, so it moves on. Next in the list, the linear search compares 1 with 5. There is still no match, so again it moves on. Now it compares the next number, 5, with the target value, 5. This time they match. The search is successful and the algorithm stops. The program's output now says number found at index 3. Let's summarize what you've just learned about a linear search. The dataset doesn't need sorting for the algorithm to work. The algorithm loops through the array by iterating over each element, comparing the current element with the target value. If a match is found, it returns the element's index. If it isn't found, the loop completes without finding the target and returns -1. In your example, if the target number of 5 isn't found, it indicates that the number isn't present. The time complexity of linear search is O(n, O(n, O(n), where n is the number of elements in the array. So, when should you use a linear search? Use it when you have short lists or unsorted data. While it may not be the fastest approach, its simplicity makes it an excellent choice when ease of implementation takes precedence over speed. While a linear search is simple and easy to implement, it does have its drawbacks, especially with larger datasets. It is inefficient with large lists because it checks every item. If the list is long and the target item is near the end or not present, the search can take a lot of time. It's also not suitable for sorted data. If the data is sorted, use other search algorithms, like the binary search algorithm. The linear search, while basic, is a valuable tool for developers. It's easy to understand and implement, making it a great starting point for understanding search algorithms. By now, you're familiar with linear search and know it isn't the most suitable algorithm for long lists or large datasets. In this video, you'll explore the concept of temporal or time complexity, which refers to how the algorithm's running timescales with the size of the input data. In simpler terms, it measures how much longer a task will take as the task itself gets bigger. The time required for a linear search increases directly with the length of the list, as indicated by the formula O of n. The O means order of, and the n tells you how many items are in the list. For example, if the list contains 10 items, it might take up to 10 comparisons to find the desired item. Similarly, with 1,000 items, the search could take as many as 1,000 comparisons. To demonstrate how time complexity works in a linear search, write a Java class, linear search time complexity example. It will have a linear search method. It performs the search and counts how many comparisons are made. The method will return the maximum number of comparisons to find the target inside the array. Its parameters contain an int ARR, the array that is searched, and an int target, the number you're trying to find. Let's understand how this works. The int comparison equals 0 semicolon indicates the variable that keeps track of how many comparisons are made. The for loop goes through each element in the array. For each element, the comparisons plus plus increases the comparison count by 1. The program checks if the current element equals the target number. If it finds the target, it returns the number of comparisons made so far. If the loop finishes and doesn't find the target, the method returns the total number of comparisons made during the search. Now, write the main method to set everything up. The program performs several actions. First, it creates 3 arrays of different sizes. The small array contains 10 numbers already filled with values. The medium array has 100 spaces that need numbers filled in. There's also a large array, 1,000 spaces, that also need filling. The program fills the medium and large arrays with values from 1 to 100 and 1 to 1,000 respectively. Each array element is filled with numbers in increasing order in these loops. The first loop fills the medium array, and the second loop fills the large array. The second action requires the program to set the target value being searched. In this case, it's 50, which is the number the program will search for in all 3 arrays. Finally, the program then calls the linear search method 3 times, once for each array, and prints how many comparisons it took to either find the target or finish searching the entire array. Let's break down what happens in each array. Suppose you have a list of 10 elements. In this example, the last number in the array is 10. So for the program to find the target value of 10, it would first check all 9 elements before finally finding the target at the 10th position. Now imagine a list with 100 elements. If you're searching for the number 100 at the end of the list, the linear search will check all 99 elements before it reaches the 100th one. Finally, consider a list with 1,000 elements. If you're searching for the number 1,000, the linear search will go through all 999 preceding elements before finding the target. For each search, the program prints out the number of comparisons needed to find the target or finish searching the entire array. The reason linear search is O of n is because, in the worst case, you might have to check every element in the list to find the one you're looking for, or to confirm that it's not in the list. This is a direct relationship. If the number of elements doubles, the maximum number of comparisons also doubles. Linear search is simple to construct and works well with small or unsorted lists. But because it has an O of n time complexity, the time it takes to search increases as the list grows. If you anticipate working with massive datasets, understanding the time complexity may lead you to investigate more efficient search algorithms, such as binary search, which has a time complexity of O of log n and scales considerably better with larger datasets. Knowing which algorithm to use and when comes with experience. You will soon learn which to use when given a scenario. Keep learning and growing your skills. Repeatedly finding specific data in large datasets is a common challenge. When those datasets are sorted, efficiency-minded developers rely on binary search algorithms to get the job done. In this video, you'll learn how binary search's divide and conquer approach makes searching sorted data a breeze. Binary search is an efficient algorithm to quickly find a target value in a sorted list or array. It does this by repeatedly halving the search space. If a target is smaller than the middle value, the search space is halved again. The process repeats, halving the search space until the target is found or the list is empty. If the target value is found, the algorithm returns its position in the list. If the search interval is exhausted and the target isn't found, the algorithm concludes the target is not in the list. Let's turn to Java now and see how binary search works with an example. For this demonstration, we'll create a Java class called binary search demo. It has 2 key parts, the main method, which starts the program, and the binary search method, which performs the search. The binary search method performs the actual binary search. The parameters here are int array r, the sorted array to search, and int target for the number to find. The method divides and eliminates sections of the array. The method uses 2 pointers. Left points to the start of the array and right to the end. A while loop continues checking the middle element and updating the pointers until the target is found or the search ends. The middle or mid index is calculated. If the middle element equals the target, the method returns the index mid. If not, it updates the left or right pointer and continues the search. If the target is greater than the value at the middle index, the program eliminates the left half and updates the left pointer to mid +1. Continuing the search in the right half. If the target is smaller than the middle element, the program eliminates the right half and updates the right pointer to mid-1, continuing in the left half. If the while loop finishes without finding the target, meaning left has become greater than right, the method returns -1, indicating that the target number is not in the array. Next, write the main method that includes the array and target number. These two values are passed to the binary search method to find the target's index or determine it isn't in the array. Here is where you set up the array and the target number you want to search for. First, the array. This is a sorted array of integers from 2 to 99, meaning the numbers are arranged in increasing order. The fact that the array is sorted is important because binary search only works on sorted data. Let's say the target number is 23. The program calls the binary search method and passes the numbers array and the target number as arguments. The result will be the index position of the target in the array, or -1 if the target is not found. If the binary search method returns -1, it means the target number was not found in the array, and the program prints number not found. Otherwise, the program prints the index where the target number was found. What the binary search algorithm is doing here is quite simple. With the array and target number in mind, it's starting with the middle element, 45. And since 23 is smaller than 45, it focuses on the lower half of the array. Next, the middle element of the sublist is 7. Since 23 is greater than 7, focus on the upper half, so the third and fourth positions, 10 and 23. Finally, the search starts its next pass with the closest middle element, which is our target number, 23, at index 4. This approach to search isn't for unsorted lists, but for large sorted datasets, it's the most efficient. The time complexity of binary search is logarithmic, meaning the search time increases at a much slower rate compared to the size of the dataset. In other words, even as the dataset grows, binary search dramatically reduces the number of comparisons needed to find the target. For large-scale and high-performance applications, it's perfect. While binary search is ideal for large, sorted datasets, not all data is sorted or extensive. In such cases, a linear search becomes the more practical option for unsorted data. However, if sorting the data first is feasible, binary search can once again be the more efficient choice. Additionally, when working with more complex data structures, implementing binary search becomes significantly more challenging compared to the simplicity of linear search. For large sorted datasets, where searches need to be performed repeatedly and efficiently, binary search is the ideal choice. By halving the search space with each step, it significantly reduces the number of comparisons, making the process both faster and more effective. Binary search plays a key role in solving real-world challenges, from optimizing search engines to enhancing database queries. And now it's a valuable tool in your coding toolkit. I'm thinking of a number between 1 and 100. If I tell you whether your guess is higher or lower, what's the fastest way to find it? You could count up from 1 or down from 100, or guess randomly. But the most efficient way is to start in the middle, 50, and halve the options with each guess. This is how binary search works, quickly narrowing down possibilities. In this video, you'll learn how binary search uses this strategy and why its time complexity, O of log n, makes it so efficient for larger datasets. Time complexity helps explain how an algorithm's runtime changes as the input size grows. For binary search, the time complexity is O of log n, meaning that as the list gets larger, the time required to find an item increases much more slowly, following a logarithmic rate. Let's break down what O of log n means, with examples that show how binary search stays efficient as datasets grow. We'll use a Java class called binary search complexity, which is a method to calculate max comparisons. This method takes an integer and returns the O of log n value for that input. This method calculates the maximum number of comparisons binary search requires, depending on the size of the array n. In binary searches like this, each comparison eliminates half of the array. The number of comparisons depends on how many times the array can be halved. The formula mat.log of n divided by mat.log of 2 gives the base 2 logarithm, which shows how often you can split the array. For example, if the array has 8 elements, you can halve it 3 times. So, in the worst case, it would take 3 comparisons to find your target. Next, we'll write the main method, which creates an array with values 10, 100, and 1000. Each value is passed to the calculate max comparisons method, and the results are looped through. The main method sets up an array, called sizes, that contains the values 10, 100, and 1000. For each size, the number of comparisons required by binary search is calculated and the results are displayed. This for each loop goes through the array sizes 10, 100, and 1000 and calls calculate max comparisons for each. It will print the result for each value. For an array of size 10, binary search might require up to 4 comparisons. For size 100, it could take 7 comparisons, and for size 1000, up to 10 comparisons. Let's look at lists with 10, 100, and 1000 elements to further illustrate how binary search affects time complexity in practice. Take a sorted list with 10 elements. In the first comparison, check the middle element at the 5th position. Depending on whether the target is smaller or larger, look at the middle of the remaining halves. So, either the 2nd or 8th position. Repeat this process, halving the list with each step until you find the target. In the worst case, how many steps will it take? The time complexity is O of log 10, or approximately 3.32. This means binary search will require about 3.32 steps to find the target in a list of 10 elements. Now consider a sorted list with 100 elements. Binary search will use the same method, but the number of comparisons, or passes, increases slightly because the list is larger. In the first comparison, check the middle element, the 50th position. Depending on the target value, check the middle of the remaining half, either the 25th or 75th position. Continue halving the list with each step until you find the target. The time complexity for this process is O of log 100, approximately O 6.64. So the worst case here will take 7 comparisons. What about a list that has 10 times as many elements? Once again, binary search keeps halving the list until it pinpoints the target value with minimal comparisons. With 1000 elements, the worst case is closer to 10 comparisons. Looking at lists of 10, 100, and 1000 elements shows how binary search scales with larger datasets. The magic of O of log n is that even as the list size grows dramatically, the number of comparisons increases very slowly. This makes binary search incredibly efficient, especially for large datasets. In this video, you learned how binary search's method of halving the search space drastically reduces the steps needed to find an element. The larger and more sorted the list, the more time-efficient binary search becomes. Oh, and the number I chose at the beginning? 42. The way a dataset is organized, whether sorted or unsorted, can drastically change how efficiently we can search through it. This is where the choice between linear search and binary search comes into play. In this video, we'll compare the performance of linear and binary search on sorted and unsorted data, and how the size of a dataset could influence your decision. Let's start with unsorted data, where the items are in no particular order, like randomly arranged books on a shelf. In this case, linear search is the only option. Why? Without any indexing, binary search has nothing to guide it. There's no way to divide the data in half, so each item must be checked one by one. In practice, the most effective choice would be a program like this, that starts with, say, a class called linear search books. Inside it, we have the linear search method and the main method. String books is the array of book titles you're searching through, and string target is the book title you're trying to find. The program uses a for loop to check each book in the array. It compares the current title with the target using the equals ignore case method, which ignores case differences, like whether Moby Dick starts with an upper or lowercase letter. If the target is found, the method returns its index in the array. If not, it returns -1, indicating the book wasn't found. The method will have a string array of books and a string target set to Moby Dick. Both will be passed as arguments to the linear search method. The program starts by creating an array of book titles, like a list of books on a shelf. It then searches through this list to find a specific one. If the target book is Moby Dick, it passes it to the linear search method. This line calls the linear search method passing the array and target title. It returns the book's index if found, or a -1 if it isn't. For unsorted data, linear search checks each item one by one. It's the default choice for smaller lists. But what about larger unsorted lists? Even with hundreds of unsorted books, linear search is the better option since binary search requires sorting. While binary search can start with unsorted data, linear search becomes inefficient with sorted data. To see binary search in action, let's switch to an alphabetically organized list of books. A binary search of sorted data like this might have a Java class called binary search books. Inside the class, the binary search method takes 2 arguments. Books is the sorted array of book titles, and target is the name of the book being searched for, in this case, Tolkien's classic, The Hobbit. Using binary search, the algorithm starts by checking the middle of the list and then determines if The Hobbit is in the first or second half. It continues halving the list until it finds the target or confirms it's not there. To help you choose the right algorithm, let's summarize the best use cases for each. In general, for unsorted lists, linear search is the clear best option, since binary search requires the data to be sorted. But if the data is already sorted or can be sorted first, binary search is much faster. However, the size of the dataset does add some nuance to the choice. So, for small, unsorted datasets, like a few randomly arranged books, linear search is simple and effective. For large, unsorted datasets, linear search can still be used, but sorting the list first could save significant time on repeated lookups. That's because, for sorted lists, binary search is the clearer choice for efficiency. Although, if the dataset is very small, like an unsorted shopping list of 10 items, linear search may still be simpler and shouldn't be completely ruled out. Finally, for large, sorted datasets, binary search is the clear winner. Its method of halving the dataset with each step drastically reduces search time and makes it the most efficient choice. In this video, you've seen a comparison of linear and binary search, focusing on their efficiency in different scenarios. By understanding the dataset size and whether it's sorted or unsorted, you can make better decisions about which algorithm to use for optimal performance. Happy searching. Think about your workspace after a long day. You might have documents, stationery, or other items scattered around. To quickly locate what you need, it's much easier when everything is organized and in its proper place, right? While sorting algorithms can't organize your physical workspace, they can perform a similar function for data. They streamline the process of finding and using necessary information quickly, which is particularly valuable for organizations developing efficient applications. Sorting algorithms act as a set of instructions that organize information in a precise and efficient order. When data is sorted, whether it's numbers, words, or objects, it is arranged in a sequence, such as from smallest to largest, or alphabetically. This is important because sorted data is easier to manage, search, and analyze. In this video, you will learn how sorting works, how it helps solve problems more efficiently, and how it applies to everyday life and computing. Sorting is a fundamental concept because it helps in organizing information. This is extremely valuable because data needs to be accessed and used effectively. Let's imagine a few scenarios where sorting makes life easier. Take a library, for example. Books are typically organized by the author's last name, genre, or title, making it easy to find what you're looking for. If the books were placed randomly on the shelves, finding a specific one would take much longer, leading to less effective learning. Your phone's contact list is another great example. Typically, contacts are sorted alphabetically, making it easy to scroll and find the person you want to call or text. Now, if the contacts were in a random order, locating a specific name would be frustrating and time-consuming. And if you've enjoyed a seamless online shopping experience, you can thank sorting algorithms. They allow you to sort items by price, customer ratings, or popularity, helping you find the products that best suit your needs. For example, if you're searching for the most affordable option, you can easily sort items from lowest to highest price. As a final example, educators and administrators often sort students' grades from highest to lowest. This makes it easy to review individual performance relative to others and identify trends across the class. Sorting isn't just about convenience, it's about efficiency. In computers, sorting is crucial because it makes searching and organizing data much faster. If you have a list of thousands of names and you need to find one specific name, a sorted list allows the computer to find it quickly without having to check every single name. That's time-saving and valuable. But how do they work exactly? Simply put, sorting algorithms are the step-by-step methods computers use to organize data. Once organized, the data can be accessed or edited quickly and easily. Each algorithm uses a unique technique for sorting. So let's look at some of the most popular ones to understand how they work. For example, bubble sort is one of the simplest sorting algorithms. Imagine you want to sort a deck of playing cards based on the number of the card. A bubble sort algorithm starts by comparing the first two cards. If the first card is larger than the second, it swaps and reorders them. It then moves to the next pair. This process is repeated until all the cards are arranged from smallest to largest. And as it continues with new entries, smaller cards move or bubble to their place in the order. Bubble sort algorithms are used in applications where simplicity and ease of implementation are essential. Their ease of understanding and implementation makes them particularly useful for small datasets or when the dataset is nearly sorted. Another key sorting method is selection sort. It works in sequence by finding the smallest number in a list and moving it to the front. Then it looks for the next smallest number and places it next in line. A selection sorting algorithm starts by picking out the card with the lowest value and moving it to the leftmost position. Then it looks for the next lowest card and places it right after the first one. The process continues until all the cards are arranged from lowest to highest value. Selection sort algorithms are ideal for situations where memory usage is a concern because they minimize the number of swaps. They're particularly useful in scenarios where the dataset is relatively small or where simplicity and predictability in performance are more important than speed. Another useful method is the insertion sort, which organizes data by gradually building a sorted list, inserting each new element into its correct position. If the algorithm starts with one entry and then another comes along, insertion sort places the new entry in its correct position relative to the first. It keeps adding incoming entries one by one, placing each in the right spot until your list is fully organized. With insertion sort, the algorithm takes each value or number from an unsorted list and inserts it into its proper place within a growing ordered list. This process is repeated until the entire list is sorted. Insertion sort algorithms are particularly effective for small or partially sorted datasets. Its simplicity and efficiency make it ideal for real-time applications with limited computational resources, such as embedded systems or manual data entry. Apart from bubble, selection, and insertion sorts, there are many more sorting algorithms worth experimenting with, each with their own strengths and unique applications. The bucket sort groups elements into buckets before sorting. Merge sort divides the list and merges the sorted parts. Radix sort processes numbers by each digit, useful for sorting large numbers or data with a significant range of values. And quicksort is known for its efficiency in partitioning and sorting segments. Sorting algorithms are widely used in real-world applications, playing a crucial role in organizing and processing data across various fields. From social media fields that sort content by recency, or engagement to music streaming services like Spotify that help you discover your next favorite song, these algorithms are integral to our daily digital experiences. Whether it's sorting names, numbers, products, or posts, these algorithms are at the core of many everyday tasks and computer processes. In this video, you learned how key sorting algorithms work, why they're efficient, and how crucial they are to solving real-world challenges. If you understand sorting, you can better grasp how computers solve problems and organize information. This gives you the critical insight to optimize data processing and improve decision-making in any application you choose to develop. You walk into a library and find all the books on a shelf in disarray, some tall and some short, randomly placed. You've been asked to organize them by height, from the shortest to the tallest. Arranging these books neatly not only makes the shelf look tidy, but also makes it easier to find books in the future. In this video, you will learn how to use the bubble sort method to sort items effectively, just like organizing books in a library. Looking at the shelf, you notice the books are in random order. You aim to arrange them so the shortest book is on the left side of the shelf and the tallest book is on the right. This task is similar to sorting data. You will use the bubble sort method, a straightforward approach perfect for small data sets. You begin by comparing the first two books. If the first book is taller than the second, swap their positions, placing the shorter one on the left. Then, compare the second book with the third. If no swap is needed, you will move to the next pair. Keep swapping until you reach the last element. This is known as the first pass. By this first pass, the tallest book will have bubbled up to the end of the row. This mirrors how bubble sort works in programming, iteratively comparing and swapping items to sort a list. With the tallest book in the correct position, repeat the process for the remaining books, known as a pass. ignoring the last one because it's already in its proper spot. You start again from the first book, comparing and swapping if needed. With each pass, the next tallest book moves to its correct position. This process gradually sorts all the books until the shortest is on the far left and the tallest on the far right. You continue repeating the sorting process, each time considering one less book. Eventually, no more swaps are needed, and the books are perfectly sorted from shortest to tallest. So what reflections can you draw from this example? The bubble sort algorithm made the task simple. It required no complex thinking, only comparing and swapping as needed. While it may take longer with more books, bubble sorting is easy to implement for small data collections. Now let's take this into Java and translate the sorting method into code. First, create the main class to start coding. Define an array of integers representing the height of each book in centimeters. Next, the modularity of the code can be enhanced by segregating the frequently used methods. For instance, you'll print the array twice, that is, before and after the sorting. Writing a dedicated method that handles printing the array elements is better, which you can call from the main method function whenever needed. Now you need to call this method to print the array from the main method. This is where the magic of sorting happens. You have to write a separate method to execute the sorting, which is as follows. Name the method as bubble sort and pass on the array. Then call the method from the main method. Now that you have sorted the array, you need to print and check if the array element has been sorted. Here you again need to call the printHeight method to print the sorted array from the main method. Once you run your program, you'll have the following output, which lists the books in height from shortest at 12 centimeters to tallest at 15 centimeters. Great job! You now know how to use the bubble sort method in Java, which allows smaller elements to bubble up to the correct position through repeated comparisons and swaps. While it's simple and easy to understand, you also discovered that it might not be the most efficient choice for larger datasets. However, it's a great way to get started with sorting algorithms. It provides valuable insights into how sorting works and can be applied in everyday situations like organizing a bookshelf. Tony invited his friends over for a card game. He was dealt a hand of shuffled cards and wants to sort them in ascending order, from the lowest to the highest value. You can sort cards based on the card value or the suit. Tony decides to sort the cards based on the card or number value. Therefore, the number 2 is ranked the lowest and 10 is the highest. A card with the lowest value is 2 and an ace has the highest value. Can you write a Java program to help Tony sort his cards? In this video, you'll learn how to apply the insertion sort algorithm, simulating how people arrange cards based on card number ranking. The pack of cards only contains number cards. First, let's view Tony's initial hand. He has 5 cards, 7 of spades, 3 of diamonds, 10 of clubs, 5 of hearts, and 2 of spades. Sorting the cards by hand requires Tony to pick up a card and place it in the correct position relative to the first card on the left. He will continue this process until all the cards are sorted. Tony starts by considering the first card, the 7 of spades. Since it's the only card, it's already sorted, so no action is needed. The second card is the 3 of diamonds, which is smaller than the 7 of spades. Tony moves the 3 of diamonds to the left of the 7 of spades. His hand is now 3 of diamonds, 7 of spades, 10 of clubs, 5 of hearts, and 2 of spades. The third card is the 10 of clubs, ranked higher than the 7 of spades. Therefore, the card is in the correct position and no sorting is needed. The fourth card is the 5 of hearts. 5 is smaller than 10 and 7 but greater than 3. Therefore, Tony inserts the 5 of hearts between the 3 of diamonds and the 7 of spades. The last card is the 2 of spades. 2 is smaller than 3 and Tony moves the card to the left of the 3 of diamonds. His hand is now sorted from lowest to highest, as the 2 of spades, 3 of diamonds, 5 of hearts, 7 of spades, and 10 of clubs. How does this relate to a Java program? The insertion sort algorithm can simulate the sorting of the cards. Navigate to IntelliJ to explore the insertion sort algorithm in 4 steps. Step 1. You have to create the main class and define an array of integers to store the numbers on the cards. Call the printArray method to display the initial array. You can then compare the before and after sort outputs. The insertion sort method will sort the card values in ascending order. Insert another print array to view the sorted cards. Step 2. Insert a print array method consisting of a for loop to iterate over each element in the cards array. The cards variable represents each card value during each iteration. The print method will indicate each card value followed by a space for readability. Outside the for loop, insert a print line statement to view the output on a new line. Step 3. Insert another method and call it insertion sort. This method has a for loop that starts from the second element, index 1, and iterates through each element in the array. The purpose of this loop is to pick each card one by one and place it in its correct position relative to the already sorted part of the array. The current card variable stores the value of the current element that needs to be placed in the correct position. Next, insert a while loop as an inner loop. This loop checks if the current element is smaller than the elements in the sorted part of the array from the left side. If so, it shifts the larger elements one position to the right to make space for current card. Therefore, cards counter 2 plus 1 equals cards counter 2, indicates the larger elements are shifted from one position to the right. The counter 2 indicates the decrementing counter and checks the next element on the left. After finding the correct position, the current card is inserted into its appropriate position within the sorted portion of the array. Step 4. Let's view the output. Java sorted the cards just like Tony did. In this video, you learned that the insertion sort method simulated how Tony sorted his cards by placing each new item in the correct position relative to the other cards. Although insertion sort might not be the fastest algorithm for large datasets, it is highly effective and easy to understand for smaller or nearly sorted lists, making it a perfect choice for Tony's task of organizing his hand of cards. Have you played a game where you have to sort items based on size, color, or value? Many games advertise that sorting items can increase your IQ, as it keeps your brain active. Ashley has 5 coins of different sizes and wants to arrange them from smallest to largest. The diameters of the coins are 25, 15, 30, 20, and 10. Can you help Ashley write a Java program that can sort the coins? In this video, you'll learn how to apply the selection sort algorithm, simulating how people arrange coins based on size. First, let's look at how Ashley will sort the coins by hand. She randomly places the coins on a table. The order, based on diameter in millimeters, is 25, 15, 30, 20, and 10. Ashley picks up the smallest coin, the 10 millimeters, and swaps it with the first coin, the 25 millimeter. The order of coins is now 10, 15, 30, 20, and 25. The smallest coin is in the correct position. Next, she looks at the remaining coins and selects the 15mm one as the smallest. Ashley notices that the coin is in the correct position, so swapping coins is unnecessary. The last 3 coins are 30, 20, and 25. Ashley selects the 20mm coin and swaps it with the 30mm coin, so the order of the coins is now 10, 15, 20, 30, and 25. Lastly, she swaps the 30mm with the 25mm. The order of the coins is now 10, 15, 20, 25, and 30. Ashley has sorted the coins from smallest to largest based on their diameter. How does this relate to a Java program? You can use the selection sort algorithm to simulate the sorting of the coins. The algorithm will split the list into 2 groups, a sorted group to the left and an unsorted group to the right. Similarly to what Ashley did, the algorithm will take the smallest size from the unsorted group and place it in the sorted group. When all the coins are sorted, the algorithm will stop. Navigate to IntelliJ to explore the selection sort algorithm in 4 steps. Step 1. You have to create the main class and define an array of integers to store the size of the coins in millimeter. Call the printArray method to display the initial array. You can then compare the before and after sort outputs. The selection sort method will sort the coin sizes in ascending order. Insertion of the printArray to view the sorted cards. Step 2. Insert a printArray method consisting of a for loop to iterate over each element in the sizes array. The sizes variable represents each coin size during each iteration. The print method will indicate each coin size followed by a space for readability. Outside the for loop, insert a print line statement to view the output on a new line. Step 3. Insert another method and call it selection sort. The length of the sizes array is stored in the variable named length. The for loop starts from the first element, index 0, and iterates through each element in the array up to the last element, or length -1. This ensures that the outer loop controls the boundary between the sorted and unsorted groups of the array. After each iteration, one more element is added to the sorted group. The algorithm initially assumes that the first element in the unsorted portion, or counter, is the smallest. The index of this element is stored in min-index. The inner loop will start from the element right after the counter and go to the end of the array. The if statement compares each element in the unsorted group with the current minimum. If a smaller element is found, the min-index is updated to this new index, as indicated by the new counter. The smallest element, found in the unsorted group, located at min-index, is then swapped with the first unsorted element, located at counter. The value at sizes, min-index, is then temporarily stored in temp and replaced with the element at sizes, counter. Lastly, this element is then stored in temp. The outer loop continues, moving the boundary between the sorted and unsorted groups to the right, one by one, after each iteration until the entire array is sorted. Step 4. Let's view the output. Java sorted the coins just like Ashley did. In this video, you learned that the selection sort method simulated how Ashley sorted her coins. The algorithm repeatedly scanned the unsorted portion of the list to find the smallest element. Although selection sort is easy to interpret and implement, it is not the most efficient algorithm for large data sets. However, its simplicity makes it an excellent choice for small lists or when an easy-to-implement sorting method is needed. Sorting is an essential process in programming. It allows you to organize, prioritize, retrieve, and make sense of information and processes. With sorting, you can also group data for problem solving, optimization, and further processing. There are 3 basic Java sorting algorithms: bubble, insertion, and selection sort. With bubble sort, each element is compared with its adjacent element, and if they are in the wrong order, they're swapped. This process is repeated iteratively until the list is sorted. Insertion sort divides the list into a sorted and unsorted group. An element is taken from the unsorted group and placed in the correct position of the sorted group. This process is repeated until all the elements are sorted. Selection sort selects the smallest element from the unsorted group and moves it into its correct position of the sorted portion. This process is repeated until all the elements are sorted. In this video, you'll compare the 3 algorithms based on time efficiency, complexity, and use cases. Understanding time complexity helps you choose the most efficient sorting algorithm based on the size and nature of the data you're working with. Time complexity indicates an algorithm's time to run with large or complex data sets. In the context of Java sorting algorithms, time complexity describes the efficiency of different sorting methods. Time complexity is described with the big O notation, or big O of n. It provides an upper bound on the growth rate of an algorithm's running time, or memory usage, as the size of the input data increases. The n indicates the size of the input data, or the number of elements in an array. The big O of n denotes a linear relationship between the input size and the time required to process that input, making it straightforward and predictable regarding time complexity. You need to know all 3 algorithms' best and worst case scenarios. Let's explore examples of best and worst case time complexity for the 3 sorting algorithms. The selection sort has the highest time complexity for 5 elements, making it the least preferred option. Let's start with bubble sort. Big O of n denoted the best case scenario, indicating that the list is already sorted and no swaps are needed. For the worst case scenario, the list is sorted in reverse order. Therefore, each element is out of place. Bubble sort will require n-1 passes through the list, with each pass making approximately n comparisons. Therefore, the number of operations is proportional to n multiplied by n-1 divided by 2, simplifying to big O of n squared. In practice, even in a best case scenario, most implementations of bubble sort still perform big O of n squared operations unless optimized with a flag to stop early. It's important to note that bubble sort is rarely used in practice due to its generally poor performance, even with the early termination optimization. So, why perform big O of n squared operations? The nested loop structure of bubble sort, where one loop controls the number of passes and the inner loop performs the comparisons, leads to a quadratic time complexity of big O of n squared. This means that if the input size doubles, the time taken increases 4 times. The second algorithm is the insertion sort. O of n denotes the best case scenario, as the list is nearly sorted. Each new element is placed directly after the previous one, requiring only one comparison per element, and the number of operations is linear. In the worst case scenario, each element must be compared with all the previously sorted elements, leading to n comparisons for each insertion. This results in big O of n squared time complexity. Similar to bubble sort, insertion sort has a nested loop structure. The outer loop iterates over the elements, and the inner loop compares and shifts elements to find the correct position, leading to a quadratic time complexity. The third algorithm is the selection sort. Interestingly, selection sort always scans the entire unsorted portion of the list to find the smallest element, regardless of whether the list is already sorted. Therefore, time complexity is always big O of n squared. The algorithm makes n comparisons in each pass to find the minimum element. Since this process is repeated for each element in the list, the total number of comparisons leads to a quadratic time complexity. Let's review the time complexity of the 3 algorithms. Big O of n indicates a linear time complexity as time grows linear to the input size. This is the best case scenario for bubble sort and insertion sort, where the list is nearly sorted. Big O of n squared indicates a quadratic time complexity with time that grows quadratically as the input size increases. This occurs when the list is not sorted and the algorithm must perform many comparisons, swaps, or shifts. In this video, you compare the time complexity of the 3 basic Java sorting algorithms. Understanding time complexity helps in choosing the correct algorithm based on the nature and size of the data, allowing for more efficient sorting in practical applications. Insertion sort is often the best choice for small or nearly sorted datasets because it can perform close to big O of n. Bubble sort is also effective for nearly sorted lists, though it is generally slower than insertion sort due to more comparisons and swaps. Selection sort is straightforward, but consistently slower with the time complexity of big O of n squared, regardless of the dataset's initial order. Happy coding! Congratulations! Through hard work and effort, you've reached another milestone in your learning journey. You've completed Course 3 on data structures and algorithms and, along the way, gained essential skills in building efficient, scalable applications. You will shortly put all that you've learned so far into practice, working through an interesting and challenging project. But before you do, let's take a few minutes to review the highlights and key takeaways of this course. Module 1 introduced you to some fundamental data structures in Java, including arrays, array lists, linked lists, stacks, and queues. It began with the basics of arrays. You learned that arrays are fixed-size data structures that store elements of the same type. Arrays provide efficient storage and fast access. Your next step on the learning path was an examination of array lists, a dynamic alternative to arrays. You discovered how these dynamic data structures offer flexibility in managing collections of data. Unlike arrays, array lists can grow and shrink, making them perfect for when the number of elements isn't known upfront. From there, you moved on to tackling linked lists. You discovered that these were linear data structures where each node points to the next. You explored both singly linked lists, where each node only points forward, and doubly linked lists, where nodes point both forward and backwards. Then came an introduction to the concepts of stacks and queues. In particular, you mastered their use in scenarios that require last in, first out, LIFO, and first in, first out, FIFO operations. As you discovered, stacks follow the last in, first out, or LIFO principle, and you observed how this works in practice. On the other hand, queues follow the first in, first out, or FIFO principle, which makes them ideal for systems where elements are processed in the order they arrive. As always, this knowledge was grounded firmly in the context of real-world scenarios and practical exercises. In Module 2, you extended the boundaries of your knowledge even further. You were introduced to advanced algorithms in Java, focusing on efficient data management and retrieval techniques. You learned about 3 important structures: HashMap, TreeMap, and LinkedHashMap. You discovered what these are, and also how they can be implemented in a practical way to optimize data storage and access. Another key topic covered was searching algorithms, and you learned how to implement both a linear and a binary search for quick data retrieval. This module also covered a range of sorting algorithms. You explored the concepts behind them and discovered their practical applications. You explored sorting methods, such as bubble, insertion, and selection. To handle larger datasets efficiently, you learned about more advanced sorts, such as the merge sort and quicksort methods. You finished this module with new and valuable skills to implement and optimize algorithms for enhanced application performance. Module 3 focused on essential software testing practices. It began with the fundamentals of software testing and demonstrated the role of testing in ensuring that you develop and release high-quality code. It explained that the testing can be manual or automated testing. Manual testing is ideal for exploratory and usability testing, while automated testing is more efficient for repetitive checks and large-scale test execution. You also gained key insights into functional versus non-functional testing, as well as contrasting black box and white box techniques. Next, exploring JUnit and GitHub reinforced the importance of version control. Another key testing tool this module introduced you to was JUnit, which provides a framework to perform testing. JUnit's annotations, such as @test and lifecycle methods like @before and @after, introduce you to new ways to organize and control test execution. These features gave your testing process greater flexibility and precision. Having gained an appreciation of the importance of testing, you learned about another important tool in your software developer's toolkit: test-driven development, known as TDD. It can also be described as the Red-Green-Refactor cycle. Demonstrations and practical exercises showed the advantages of writing tests before code. As a developer, this approach of early testing provides rapid feedback and helps you to design effective and focused code. The knowledge and hands-on experience you've gained in this course will help you to approach complex problems with confidence and use the right data structures and algorithms to create robust and efficient solutions. As you move forward in your learning path, continue to practice and apply what you've learned. These techniques will be invaluable in any programming or software engineering role.
So my name is Joy, and I am a software engineer, as I guess we call them software development engineer at Amazon. I guess I'm an SD2, so I'm a little bit more senior than the new hires. I've been here for about 3 years, and before that, I was at Google for 4 years. As a more senior engineer, I spend about at least 40% of my time during doing meetings. So we've got meetings for stand-up where our team kind of talks about what we're all doing. I've got design review meetings where either I'm presenting my own designs or the team or reviewing my teammates' designs. On-call is also something that I spend time on. I'm on call right now. So on-call involves like addressing tickets from other teams or addressing tickets that are related to our product. And then the little time I have left, I actually do the things that I'm working on. So either writing my own design docs or writing my own implementation for the code that I'm working on. So for my interactions with generative AI, there are tools that are available that try to help our lives. And I think that it is helpful for others. As you become a more senior engineer, the actual amount of coding that you do is pretty minimal. So even the amount of coding that I am doing, it's like, okay, how do I onboard my system to Gen AI and then actually make it helpful? So right now at this stage, it's not very helpful for me at all. And I do also know that PMs in particular are using Gen AI a lot in order to help produce these docs and save time that hasn't been available before. So I'm sure that the people who are actually working on it would be a lot more like, oh yeah, this is the future. But for me, I am a late adopter, and I am also not, and also my team we're just not using it at all. I recognize that it's different, that the current situation right now to try to get into software development is different from when I started, which was like 8 to 10 years ago. You still want to try to get your foot into the door. And in order to do that, you've got to have the foundation of being able to code. So in order to be able to code, you've got to practice. So practice your data structures and algorithms, practice actually coding it out, writing bug-free code, and kind of thinking about the end consumer. I think that one kind of important thing, aside from practice, to perform well in your interviews is communication. Try to communicate what you're thinking, try to communicate like how you're trying to get to the solution, and don't be afraid to ask for help. And usually the interviewer will be happy to kind of step in and give you some pointers, and that's kind of what they're trained to do. And ultimately, that's what people want. That's the kind of people that we want to work with, the people who are ready to ask questions and ready to, go in the right direction. And once they have the right direction, that they're able to independently kind of figure things out. Right now, I am actually mentoring an intern. This is very hands-on mentorship where I, look at all of their documents and I kind of tell them exactly what they need to accomplish and follow up with them for each of their milestones for their project. Outside of that, I also, pre-pandemic, our school actually used to bring droves of students to my workplace, and then I would give them a tour and kind of tell them what it's like working at Google at the time, and also tell them what I did to get into Google and what I did to kind of be successful in my career. It's very fulfilling for me. So I hope that I can continue to do that in the future.
Congratulations. You have completed the Data Structures and Algorithms course. Your dedication and hard work have advanced your understanding and skills. In this course, you encountered various fundamental data structures and algorithms essential for building efficient and scalable software solutions. Starting with advanced data structures, you explored arrays, array lists, linked lists, stacks, queues, and maps. You should now understand their implementations, operations, advantages, and use cases. You then moved on to searching and sorting algorithms. You manipulated essential algorithms like linear and binary search, as well as various sorting algorithms, including bubble sort, insertion sort, selection sort, merge sort, and quick sort. You dealt with the theoretical concepts, but you also implemented these algorithms in Java, gaining hands-on experience in algorithmic problem solving. Additionally, you were introduced to basic testing methodologies. That is where you got involved with JUnit testing, test cases, and test-driven development, ensuring the quality and reliability of your code. With your newly developed skills, you should now be equipped with the knowledge and skills required to design efficient algorithms, manipulate complex data structures, and write robust, high-performance Java applications. The journey you've undertaken is a testament to your commitment to your craft. You've made outstanding progress, and your accomplishments in this course reflect your ability to conquer complex programming challenges. Your continued advancement in your Java programming journey indicates your potential. While this course may be complete, your learning journey is far from over. Continue to build on your solid foundation by exploring more advanced topics and exciting projects in Java. Keep the momentum going. You are now another step closer to achieving Amazon's professional certificate in junior software development and kickstarting your career in software development. This certificate prepares you for entry-level positions and demonstrates your proficiency and commitment to learning. Continue to progress your skills and knowledge by registering for the next course in this program. Every step you take brings you closer to achieving your goals. Thank you for your hard work and commitment. The best of luck with the rest of your learning journey as you refine your Java programming skills.
Hi, my name is James Karai. I'm a software engineer at Amazon. Introducing new people to software engineering as a career for an internship can be tricky because people learn kind of their foundational skills in all different ways. Some come from academia or going to college, and other people have just been tinkerers by nature. The important thing is understanding what skills people have and what skills people need to be successful. The biggest skills that software engineers can have aren't dealing with one specific technology. It's about understanding how to solve problems that you've never seen before. And so helping people get the skills to do that is the most important part of an internship, because then even if they don't have the technology, they know how to find the resources to unblock themselves, make it a new problem that they've never seen before. So at Amazon, interns are expected to be nearly entry-level engineers. So just by virtue of being an intern, a contribution is expected from your summer project. The first year that I was an intern mentor, I was out of the office for 2 weeks, right in the middle of summer. I had set up my intern to have success, right? And then when I was coming back, I was ready to see what had happened. And interestingly, my intern had picked up and completed way more than I had expected. I mentored a different intern who had a big project, and it ended up being really stressful. And after the internship, when we were reviewing, it turned out they were doing a little bit of work outside of working hours, and I didn't realize how stressful it was for them. And part of that is on the mentors to provide a really seamless experience, and part of that is on each of us to make sure that we find the right work-life balance. And I think the biggest advice I give to interns is to make your way in your own internship. If you need help, ask for it. If you can move faster, you should do it. It's important to take initiative, and it's important to treat it like it is a job. It's a nice way to test the waters to see if, is this a company I could work for? Is this a team I could work on? And it's also a great way to prove yourself, grow your skills, and understand where you need to grow to be successful in the ways that are meaningful to you. As an intern, similar to when you're in college, or if you're not going to college, when you're just sort of starting to figure out what you want to do, it's the best time in your life to explore and experiment and tinker with things that you maybe won't have the time to do when you're a full-fledged, working adult. There's no better time to dig into something and really understand the low-level details. And I think the people that I've seen who have done that have had a lot of success in their later careers, just because they've taken the time to grow the skills that really serve software engineers through their careers. Internships and those sort of mentorship opportunities are really important, just because software engineering is a lot of handing off, not just from older people to younger people, but just from current generation of engineers to the next. And a lot of times, maybe people don't learn so well by reading documentation or watching videos. Maybe it's really critical for people to have like a person-to-person interaction so they can learn things and be supported on that journey. I think on the other hand, software engineering is really uniquely suited where anyone with a computer, or even just access to a computer, can build something that impacts the entire world. Interning and mentorship are important, but it's nice to know that you don't have to have an internship at a big company to be a great software engineer, and you don't have to have an internship anywhere to be a great software engineer.
You're still pursuing your hobby of skydiving, and you've just performed another jump from the plane. You're confident that the pilot has lined up the drop correctly, an airfield called aero heights. Instead, when you land, you discover that there has been a navigation error, and you've been dropped in a different location. You discover that you're somewhere just inside the Smoky Mountains National Park, instead of at the airfield near Gatlinburg. You estimate that you're quite some distance away from where you should be. Luckily, you've been taught to navigate using a map, so you begin to move step by step along one of the trails. You decide that when you hit a dead end, you'll backtrack and then try another trail. If you keep this approach to finding a way back to civilization in mind, you will already have an understanding of the basic concept of TDD, or test-driven development. It also uses the principle of testing and then backtracking if you meet a dead end in order to test again. The first step is to set a specific goal for a specific class or feature. This is similar to studying your map and planning your route back to a particular target, Gatlinburg. But, despite your map reading skills, you might discover that the first trail you decided to follow leads to a dead end. If this happens, you'll need to backtrack to your original starting point. In TDD, your first approach might also fail because the functionality is not available or is implemented incorrectly. After returning to the starting point in the national park, you assess what went wrong, study the map, and choose another trail to follow to reach Gatlinburg. Similarly, in TDD, if a test fails, you would assess and modify your code to ensure that the test will pass. This is known as the green phase. By changing the code, you can address the failure without changing external behavior, improve the code design, or try a different approach. You remove the code that is not working and note it so that you don't repeat the error. If your alternative route also leads to a dead end, you would need to try another trail. In a similar way, you would try different approaches in your code to meet the expected behavior and requirements. Eventually, through persistence, discipline, and iterative testing of changes, your code will finally work, and your test will pass. You then document this progress. Finally, to your relief, you reach Gatlinburg. But now that you review your journey, you realize that there might have been a more direct way. This may happen in TDD also. Having reached this first goal may not be the end of the TDD process. You might repeat all these steps because you want to find a more streamlined or quicker solution, or you want to expand functionality. You're now safely in Gatlinburg, but, of course, you're supposed to be at the Aero Heights airfield. Now you need to repeat your mapping process to reach this additional goal. Similarly, in TDD, you might repeat the steps outlined in order to expand on the functionality already achieved. Now that you have an understanding of how the TDD process works, let's explore an accepted way to represent it. The term Red-Green-Refactor is another way of compartmentalizing and expressing the TDD process. The red phase is where you write a test for a new feature or functionality, such as add two numbers, that does not exist. The test is expected to fail, and hence the term red is used. The focus of this phase is to get the required functionality up and running. As you were following the map to get back to Gatlinburg, you would have set several interim goals, such as moving forward for 5 miles and then resting. This path has not been selected as yet, but it sets out the requirements for you to progress a certain distance towards Gatlinburg. The green phase is where you write enough code to make the failing test pass. The focus of this phase is to get the required functionality up and running. In the green phase, you may not have reached your ultimate goal, but you have progressed. In the refactor phase, you focus on improving your existing implementation. Essentially, you change the code to make it better. The objective of the refactor phase is to maintain high code quality. Once you reach your target point of 5 miles and have a rest, you will probably set a new interim point to stop and take another break. In TDD, this would begin another red-green-refactor cycle. This video has demonstrated the concept of one of the best testing methodologies, TDD, or test-driven development. It focuses on writing tests to establish the functionality required before actually writing code to make the tests pass. You also learned how this can be expressed as the red-green-refactor cycle. Hopefully, your map reading skills enabled you to return to the actual drop point by the quickest and shortest route. In the same way, you can use the TDD method to save yourself time while developing robust and efficient code. Your last skydiving trip involved navigating out of the woods and back to the intended drop site. Of course, this was an imaginary jump from a plane, but it demonstrated the process of test-driven development, or TDD, software development methodology. You also learned that this can be represented as the red-green-refactor cycle. The red, green, and refactor approach of TDD helps to compartmentalize the testing process into 3 distinct stages. The first, or red phase, of the TDD process begins with setting a goal to implement a feature or function that does not already exist. During this red phase, you create a test for the new functionality. This test is initially expected to fail. The next stage of the TDD process is the green phase. In this phase, you create the minimum code required to make the test you've created for the new functionality pass. During the green phase, your focus should be on getting the required functionality up and running in the quickest way possible. The code simply has to work without embellishment. Once the test is passed and the new feature is operational, the focus shifts to optimizing and streamlining the existing implementation. This is the refactor phase. During the refactor phase, you would focus on improving the quality of the code without changing functionality, which means that the tests still pass. At this point, you amend the code to produce the most efficient and elegant version. Let's work through an example of the red, green, and refactor stages of a test-driven development process. To prepare for this demonstration, JUnit has already been added to the project, and the test sources root directory has been marked up. The example will use a class named stringUtils that contains a method called reverseString. It will return the reverse of any string passed to it. The implementation will be done using TDD. A class named testStringUtils will be used to test the reverseString method. The test is for the class stringUtils is currently an empty class, and the class testStringUtils is also empty. Create an object of the stringUtils class named stringUtilsObject. Call the reverseString method using the object stringUtilsObject with the parameter hello. Assign the returned value to the variable result. Since the reverse of the string hello is OLLEH, assert if the returned value is equal to OLLEH. As expected, this test will fail because the method reverse string does exist in the class stringUtils. In fact, it will not compile and will be displayed in red. The red stage of TDD is now complete, since the requirement is set up and documented. Next, move on to the green stage, which is to write the minimum code in order to make the test pass. In the class stringUtils, create a method named reverseString that accepts the string parameter and returns a string. Next, create a string builder object from the string by passing the string parameter to the string builder constructor. A string is immutable. The string builder class, while it is similar, contains a mutable collection of characters, and every concatenation creates a new string. One of the ways to create a string builder is to pass a string into its constructor. Like the string class, the string builder class provides many methods to manipulate a string. Here, the reverse method reverses the string or collection of characters in the string builder object. The toString method returns a string from the collection of characters in the string builder object. Now reverse the string. Going back to the class, test stringUtils, the red marking has disappeared, and the test method passes. The red and green phases are now complete, so the third step in the TDD process is to refactor and improve the code. For example, if the string is empty, it is not necessary to create a string builder object or perform any of the steps. We can just return the empty string back. So now you will amend the code to reflect that. Also, the code contains 3 lines of code and an extra variable of the string builder class that can be condensed to this single line. This code for reversing a string works well. But what if, when it's released, someone passes null to the parameter? It's important to anticipate situations like this, and error handling would improve the code. Since this is a new functionality, it would start another cycle of Red-Green-Refactor. This video has taken you through a practical example of the test-driven development process, represented by the Red-Green-Refactor cycle. You explored setting a goal and writing a test that was expected to fail. Then, you adjusted the code to ensure it passed the test and refactored it to make the test more concise and efficient. The Red-Green-Refactor cycle is an agile and iterative process. It will enable you to create and then improve your code using a method that gives you rapid feedback. Its focus on early testing will help you to design focused code and respond to any difficulties early in the development process. Java testing is like preparing a parachute. Each individual part needs to be scrutinized before the whole thing can be assessed. This methodical approach in software development is known as unit testing. Now imagine automatically ensuring that every part of your code functions perfectly each time you make a change. That's the power of JUnit in Java development. In this video, you'll learn what JUnit is, how it supports unit testing, and how it integrates with development environments. First, what is JUnit? JUnit is a widely used framework for writing and running repeatable tests in Java. It's primarily used for unit testing, but it also supports integration testing. This is crucial for catching bugs and errors early in development. Just as a parachute is made up of parts like the canopy, pilot chute, and buckles, Java software consists of components like methods, classes, and packages. In both cases, you need to test each independent part, as well as the smallest unit of a program. For example, you might write a unit test for a method that sums 2 numbers. Testing it in isolation ensures it works before interacting with other code. JUnit is crucial for ensuring the quality and reliability of Java applications. By automating tests, it catches bugs early, making your code more robust. JUnit also supports test-driven development, TDD, where tests are written before the code, guiding the development process. For example, you can test if a method that sums 2 numbers returns the correct result. If you later change the code, JUnit quickly shows if anything broke. One of the great things about JUnit is it easily integrates with popular Java development environments like Eclipse and IntelliJ IDEA, and even build tools like Maven and Gradle. Most IDEs have built-in support for JUnit, allowing you to run tests with a single click, view results, and debug failing tests directly within the IDE. To demonstrate, let's set up a JUnit test in IntelliJ by writing a simple test for a method that multiplies 2 numbers. Start by creating a new project named JUnitDemo in IntelliJ. Then create a Java class called Calculator. Inside the Calculator class, write a method that takes 2 integers as arguments, multiplies them, and returns the result as double. Before setting up and using JUnit, you need to set a directory to use for your test classes. This directory is known as the test sources directory. Right-click on the project folder, select New, then click on Directory, name the directory test, and press Enter. The test directory will appear below the SRC folder. Right-click on it, select Mark Directory As, and click on Test Sources route. The test folder will turn green, indicating it contains all test files. Next, add the JUnit library to your project. Go to File in the menu, click on Project Structure, and in the left panel, select Libraries. Click on the plus icon at the top and select from Maven. In the pop-up, type the Maven coordinate in the box near the search button as shown. Type org.junit.jupyter:/Jupyter:5.9.1, which specifies a particular dependency in a Java project using the Maven build tool. We just specified we will use JUnit version 5.9. Now click OK. Confirm the selection by clicking OK again. The required classes will be listed. Click Apply and OK to proceed. JUnit will be added to your project, but your existing code will remain unchanged. You can observe that certain Java archive files will be listed as shown. These are the library files of JUnit. Now let's create a test class and write a method to test the multiply methods functionality. To do this, first right-click on the test directory, select New Java class, name it Calculator Test, and press Enter. Inside the class, create a test method. Type void multiply should return product of two numbers, parentheses and curly braces. Remember, test methods, also known as test cases, typically have a void return type because their purpose is to verify that the code behaves as expected. Annotate this method with @test. Then select the annotation from the org.junit.jupyter.api package within the JUnit framework. IntelliJ will automatically add the import. Inside the method, create a calculator object using the new keyword. Call the multiply method on the object by passing two numbers, such as 2 and 3, and store the result in a double variable. To verify the result, type assert equals open parenthesis, 6, product, close parenthesis, semicolon. This method compares the expected value of 6 with the actual result stored in the product variable. If they match, the test passes. If not, it fails. Notice the error? The method needs to be imported from the JUnit library. Click on the suggested import to remove the error. IntelliJ will add the required import statement. The green button next to the test case runs that specific test, while the button beside the class name runs all tests in the class. For now, either option can be used, but selecting the first one is recommended. Observe the output. It shows that the test passed, indicating the method works as expected. Perfect. In this video, you learned how JUnit is crucial for ensuring the quality and reliability of Java applications. By automating tests, JUnit helps catch bugs early, making your code more robust and reliable. Additionally, JUnit supports test-driven development, guiding the development process by writing tests before the code. And with its seamless integration into popular development environments, JUnit empowers developers to build and maintain high-quality Java applications efficiently. Remember how critical it is for a skydiver to test equipment before jumping out of a plane, and how important it is to test code before releasing it. You've already learned how to use JUnit, a key testing tool in ensuring that there is less possibility of your code showing bugs during actual running or deployment. Now you are going to learn about another useful feature in JUnit, the ability to gain additional information about code by adding annotations. In Java, annotations are like labels that you can put on your code to provide extra information. They are metadata, which describe how the methods should behave during testing. Annotations don't change how your code runs, but they can affect how tools like JUnit interpret and handle your code. So what is the correct syntax for adding annotations to your code? JUnit annotations in Java start with the @symbol. This symbol is then followed by a predefined word, such as @test. Some annotations accept parameters, while others do not. Skydivers performing safety checks on equipment will work through checklists. They may have a specific checklist for each parachute, since they may be suitable for different altitudes or wind speeds. JUnit annotations perform a similar function in software testing. Just as a checklist provides a list of what to do, annotations in JUnit tell JUnit what to do or how to perform a certain test. They help define specific behaviors and configurations. Let's examine some practical examples of these annotations in JUnit 5. Several elements are already present in the code as a starting point. It already contains a class named Calculator with a static method called add. This static method accepts two integer values and returns the sum. Imagine if one of the parachutes being checked had a large red label attached saying, "Please test this." That would certainly ensure that that particular parachute was prioritized. Adding an @test annotation to a method performs a similar task. It informs JUnit that this is a test case that it must run. Here, the test add method is marked with @test, so JUnit knows to execute this method as a test. Test code should be written inside the curly braces of this method. There are no rules as to the name of the method, but the most basic convention states using the prefix test before the method name to be tested. The @ before each annotation indicates that a method should run before each test method in the class. It can be used for common functionality like setting up common objects. There can be any number of methods tagged with this annotation, and all will execute before each method with @test, but the execution order is not guaranteed. The after each annotation is similar to a post-test inspection. If a method is annotated with after each, then it will always be executed after any test method annotated with @test is executed. It is generally used for making the environment ready for the next test. There can be any number of methods with after each annotation, but the execution order is not guaranteed. Another annotation is before all. If a method is annotated with @before all, will be run once before the first method that is annotated @test, or @before each is executed. This @before all annotation can be used only on one method, and that method must be static. Finally, the after all annotation is used for cleaning up resources, like cleaning up data and logs after all tests in the test class have been completed. Just like @before all, methods with @after all need to be static, and there can be only one such method annotated with @after all. This method runs after all the tests in the class have completed. Remember, there may be more than one method with @before all, as well as @after all, if the test class has the annotation @test_instance with the value of testinstance.lifecycle.perClass passed in the parameter. As you have observed, JUnit annotations perform several useful functions. The first is that they mark test methods. Second, the predefined word indicates the purpose of each test method. This enables you to organize your tests as well as controlling how they run. This video has explained what an annotation is. It has also explored several common ones by using annotations like @test, @before each, @after each, @before all, and @after all. By using these in your code as you move forward in your software developer career, you can make your tests more structured, reusable, and maintainable. Developers need to test every component of their code to ensure it works as intended. From methods to classes to packages, each independent component can and should be tested. While testing is crucial, it can be time-consuming. That's where JUnit comes in, offering a framework to write and run repeatable tests in Java. In this video, you'll learn how to develop a simple JUnit test case that checks if a number is even. More specifically, the objective is to test a method named isNumberEven in a class named numberUtils. In this example, the method isNumberEven takes in an integer and returns true when the number is even. Otherwise, it returns false. To ensure this method functions correctly, we're going to set up a test case for it within the numberUtils class. Having a clear objective is crucial, but writing tests is a methodical process with distinct steps to follow. A lot can ride on a single unit test, and the best results come from a thorough, well-planned approach to testing. First, you'll need a suitable test name or title. It should be descriptive and follow a consistent naming convention. In this example, the name indicates the method being tested, isNumberEven, the class it belongs to, numberUtils, and the specific condition being checked, an even value. Next, the test case needs an ID that uniquely identifies it within the project. Here, the test ID references the test case, TC, the class being tested, numberUtils, and its sequential order, 001. The objective here is to test a method named isNumberEven in a class named numberUtils. Before running the test case, there are a few critical preconditions. Number 1, ensure that JUnit 5 is properly configured, as it provides the framework for running the test. And, second, verify that the isNumberEven method is correctly set up in the numberUtils class and ready to be tested. Post conditions ensure that after the method runs, it doesn't affect other parts of the system. In this case, verify that the isNumberEven method in the numberUtils class does not alter the state of any other part of the class. With preconditions and post conditions set, the next step is to define the test data. In this case, 2 values, 4 even and 5 odd, will do just fine. These will verify if the isNumberEven method correctly identifies even and odd numbers. For the test steps, pass 4 to isNumberEven and check that it returns true. Then pass 5 and check that it returns false. For the expected results, when 4 is passed, it should return true. When 5 is passed, it should return false. Of course, the actual results can only be determined after running the tests, along with the pass or fail status, so that's next. The test method is needed to run the test. So, in the test sources directory, create a class named testNumberUtils. In this method, create a test method named testisNumberEven. This method has two assertions. One checks that 4 returns true, and the other checks that 5 returns false. This confirms the isNumberEven method works correctly for both even and odd numbers. With the test method in place, run the test by clicking on the green button. Great. Now with the actual results in hand, it's time to finish writing the test and record the results. Passing 4 returned true as expected. Passing 5 returned false, also as expected. Since the expected results and the actual results are the same, the test has passed. Perfect. The method has, in fact, been implemented correctly. In this video, you learned how to develop and write a simple JUnit test that targets a specific method. Through a step-by-step process, the isNumberEven method was tested and confirmed to be working correctly. Yes, there are other features still to test here, including tricky edge cases, but the same process and principles will apply. If you follow these steps, keep your testing simple, and approach testing methodically, you will ensure your code works as intended every time. When testing a parachute or software, each part is checked both individually and together to ensure everything works correctly on its own and as part of the whole. In this video, you'll learn how to group multiple test classes into a test suite, allowing you to run test cases together in an organized way. For example, suppose you're creating a calculator app. You start with two classes, multiplier and divisor. A test suite in Java helps ensure they work both individually and together, which any good calculator needs. To understand how test suites work, let's assume the app currently has two classes. The first is multiplier with a method called multiply2integers, which returns the product of two integers passed to it. The second class is divisor, with a method called divide2integers. This method divides the first parameter by the second and returns the result. If the second parameter is 0, it throws an illegal argument exception. Whether you're testing a parachute or an app, you should start by isolating individual components before testing them together. So first, let's focus on testing in isolation. Suppose you have two test classes in your test sources root directory, multiplier test and divisor test. The multiplier test class contains a method called testMultiply2integers, which checks if the multiplication is correct. The divisor test class contains two methods, testDivide2integerNumbers, which checks if the division is correct when valid numbers are passed, and testDivide2integerNumbers with divisor 0 throws exception, which ensures an exception is thrown when the divisor is 0. This test class uses a test method named setup. This method setup is annotated with @ before each to create an object of the divisor class before each test method runs. Suite testing is all about testing multiple components, with the power to choose which components to run together. A test suite enables developers to organize tests into manageable groups, select which tests run together, and perform integration tests. Now, to actually run the JUnit test suites, there are a few dependencies that need to be set up and checked. Most important is that the JUnit API and platform suite libraries must be compatible. The way to ensure this is to download the latest versions of both. You can set up these dependencies using the Maven build tool. When prompted in Maven, the necessary dependencies to configure are the core JUnit 5, which provides the essential annotations and lifecycle methods for unit testing, plus 4 other dependencies for running a test suite. There's one for the infrastructure to organize and run test suites, supporting annotations like @suite and @select classes. Another offers the public API for configuring test suites, including key annotations and interfaces to define which tests to run. A third contains shared utilities and functionality that support the consistent execution of test suites across different environments. Lastly, this dependency is the engine that drives the execution of test suites, managing the lifecycle and aggregating test results. Now that your dependencies are in place and configured, it's time to move on to creating the test suite itself. This involves setting up a new test class where you'll organize and manage the tests you want to run together. To do this, start by creating a new test class in your test sources folder named Calculator Test Suite and save it in a file called calculatortestsuite.java. Next, annotate the class with @suite, which tells JUnit that this class will include different test classes. It doesn't define any test itself, but instead runs tests from other classes. Now use the @select classes annotation to specify which classes should be included in the test. This annotation takes an array of classes as its argument. When we run the class, observe that the tests pass and that it has run all the test methods of both the multiplier test class and the divisor test class, as they are included in the @select classes annotation. In this video, you've learned how to group multiple test classes into a test suite in Java, making it easy to run your tests in an organized way. With the right dependencies in place, you can ensure that every component works perfectly on its own and together. With this approach, your projects will function seamlessly from start to finish. Welcome to the world of software testing. In the previous video, Types of Testing, you learned about types such as unit testing, integration testing, system testing, regression testing, and load testing. Each of these testing types is organized into stages and applied at specific points in the software lifecycle, which you covered in Course 1, Module 1, Lesson 1, Software Development Lifecycle. In this video, you'll explore the essential approaches to software testing, which involve purpose, area of coverage, techniques, tactics, focus, and perspective from which testing is done. Imagine you're at the Aero Heights Parachute Safety Festival, where the safety of every parachute is the top priority. Just as parachutes must be rigorously tested before use, your software needs thorough testing to ensure it performs flawlessly. By the end of this video, you'll understand how each approach plays a unique role in making sure your software is reliable and ready for use, just as parachutes must be before a jump. Let's examine the various testing approaches. At the festival, different techniques and approaches are used to ensure that every parachute opens properly and safely guides the jumper to the ground. These real-life testing methods and approaches will help you understand the importance of testing in software development. At the festival, you notice a plethora of testing techniques, each tailored to evaluate specific aspects of the parachute's safety and functionality. Similarly, in software development, different types of testing serve a specific purpose, ensuring that every part of the software is thoroughly examined and validated. Just as parachutes are tested in different ways based on the purpose, whether inspecting the fabric, the buckles, or the pull cords, software testing also varies depending on the focus. Manual testing involves testers carefully examining the software, focusing on specific areas based on their expertise, much like the detailed checks at the festival. However, manual testing can be time-consuming and is susceptible to human error. Just as a person might miss a small tear in the parachute fabric, a tester might overlook a minor bug in the code, leading to potential issues later on. Automated testing, on the other hand, uses tools and frameworks like JUnit or Selenium to automatically test the software. At the festival, this is like a robot named Parachecker, specifically made for parachute testing, which tirelessly checks every parachute for faults without getting bored or distracted. Automated testing is efficient and consistent, making it ideal for large-scale testing where speed and accuracy are essential. However, just like the Parachecker, automated testing is only as good as the instructions it's given. If the instructions aren't precise, some issues might go unnoticed, which could cause problems in later stages. Automated testing is excellent for performing repetitive tasks and ensuring consistent results, but it's limited by the scope of its programming, similar to how the Parachecker can only check what it's been told to. Now let's compare two other approaches to testing, functional and non-functional. Just as a parachute's primary function and performance under extreme conditions are tested, software testing uses these approaches to ensure the software operates correctly and meets all performance requirements. Similarly, functional testing ensures that the parachute deploys correctly in Java and that the user's requirements have been met. In Java, functional testing might involve using JUnit or testng to verify that each method behaves as expected. Non-functional testing, on the other hand, evaluates how well the software performs under various conditions, such as performance, stress, and high load, that are not directly associated with the user requirements. Tools like Apache JMeter and Gatling are used for this type of non-functional testing in Java. Functional testing answers the question, does the software do what it's supposed to? Non-functional testing, on the other hand, answers the question, how well does the software perform under different conditions that were not part of the user's original specifications? Suppose the testers at the Parachute Festival have no idea how the parachute components work together internally, but only what the parachute should do, which is to deploy and land the skydiver safely. This is black box testing. The testers can say that it works or does not work, but not why. In Java, tools like Selenium are used for black box testing. Now, suppose the testers at the Parachute Festival know the internal structure of the parachute and each component and how they work internally to ensure its functionality. This is white box testing. The testers can check that every part aligns with the design requirements to work as expected. In Java, most IDEs like IntelliJ provide tools to walk through the code through a process known as debugging. Also, external libraries like JACoco may be used in Java for white box testing. To sum up, different approaches or methodologies can be used to ensure the quality of the software, such as manual, automated, functional, non-functional, black box, and white box testing. Together, they ensure that your software is as reliable as a well-tested parachute. Of course, there are many other testing techniques, including regression testing, sanity testing, performance testing, load testing, security testing, and compliance testing. You'll have the opportunity to explore these techniques in future lessons. For now, this is where you take a pause. So, congratulations, you've gained a solid understanding of manual and automated testing. Thank you for following along, and best of luck with your software testing journey. Imagine this, you've just won first place in the Aero Heights Java coding contest. Your reward? An all-expenses paid trip to Aero Heights, including a 3-day stay and an exhilarating skydiving experience. How incredible is that? Aero Heights is a fictional city in the breathtaking Badlands of northern North Dakota. It is renowned as a premier destination for skydiving in the US. With its clear skies and high-altitude drop zones, it's a haven for thrill seekers and adventure enthusiasts alike. But what does skydiving have to do with Java programming? Quite a lot, actually. In the same way that a skydiver must ensure their equipment is tested and safe, a Java developer must rigorously test their code. If a parachute fails to open, the consequences could be catastrophic. While a Java program error isn't life-threatening, it can lead to significant issues if not addressed through proper testing before being used in a live environment. Just as you'd want your parachute to work perfectly during a jump, you want your Java program to run smoothly without crashing. This is where testing becomes crucial for ensuring better software. Among many other reasons, here are 4 important reasons why you have to test your code. Number 1 is safety and reliability. Just as a reliable and tested parachute ensures your safety during a jump. Similarly, well-tested software ensures the safety and reliability of an application, protecting users from crashes or data loss. Number 2 is error detection and cost reduction. Catching a parachute malfunction during a test can prevent disaster during a real jump. In software development, detecting bugs early can save time and resources, preventing costly fixes later. Number 3 is confidence and satisfaction. When your parachute has passed all tests, you can confidently jump. Likewise, rigorously tested software can be deployed with peace of mind, knowing it will perform as expected. Number 4 is continuous improvement. Just as ongoing testing and feedback enhance parachute performance, continuous testing and improvement lead to more robust and reliable software. Now that we have learned about some of the reasons to integrate testing in our software development process, let's explore some of the types of code testing while comparing them with our parachute testing analogy. First, unit testing. Imagine testing each component of the parachute, straps, buckles, cords, fabric, to ensure they're strong and reliable. In Java, unit testing involves checking individual methods or components to ensure they function correctly. Second, integration testing. Picture assembling all the parachute parts, the canopy, harness, and buckles, and testing them together. In Java, integration testing ensures that different methods, classes, and packages work seamlessly together. Third, system testing. This would be like testing the entire parachute setup, perhaps using a dummy, to ensure everything deploys correctly. In Java, system testing checks that all parts of the software work together as expected. Fourth, acceptance testing. Here, an experienced skydiver tests the parachute in a real jump after thorough checks. Acceptance testing in Java ensures that the software meets user requirements and performs well in real-world conditions. Fifth, regression testing. After several jumps, a parachute is tested again to check for wear and tear. Similarly, regression testing in Java ensures that updates or changes don't affect the software's functionality. Sixth, stress testing. Parachutes need to be tested for extreme conditions, like high winds or low temperatures. In Java, stress testing examines the software's performance under heavy data loads or other stressful conditions. And seventh, load testing. This is like checking how many jumps a parachute can handle before it fails. In Java, load testing measures the software's behavior when many users access it simultaneously. Just as thorough testing ensures a parachute's functionality works as expected and ensures the safety of the skydiver, similarly, Java code, which is tested, runs smoothly and efficiently, preventing costly errors like bugs, crashes, or unwanted deviations from the user requirements in the future. You will learn more about unit testing and how to implement it later in this course, as it forms the foundation of software testing. In this video, you learned that by making code testing a standard part of your development process, you'll create reliable and bug-free Java programs, ensuring a happy user in the same way parachute testing ensures both safe jumps and a happy skydiver. Regularly test your code. to lighten the future load. Happy testing. Congratulations on completing this penultimate module on basic testing and software development. Our goal was to equip you with the skills to produce quality, reliable code for any software challenges you face. Let's take a moment to reflect on the key insights and skills you've gained throughout this module. Your journey into software testing started with a look at the role and importance of testing in software development. Testing acts as the backbone of quality assurance, ensuring that your code behaves as expected and can scale without introducing defects. Understanding the different types of tests is essential, and you've explored unit, integration, system, and acceptance testing, each playing a critical role in various phases of development. You gained clarity on the balance between manual and automated testing by exploring when each approach is most effective. Recall that manual testing is ideal for exploratory and usability testing, while automated testing is more efficient for repetitive checks and large-scale test execution. Building on this, insight into functional versus non-functional testing, alongside contrasting black box and white box techniques, broadened your perspective on how to approach various testing scenarios. Beyond theory, you applied the practical side of testing, focusing on how to craft clear and actionable test cases. By creating well-defined descriptions, steps, and expected outcomes, your test cases became essential tools for ensuring the robustness of your code. To further enhance your testing process, automated tools like JUnit and Selenium were introduced as powerful allies in achieving efficient, reliable testing. At the same time, Git and GitHub reinforced the importance of version control and collaborative development. With a solid grasp of testing fundamentals, we shifted our focus to JUnit, the gold standard for Java testing. Instead of testing reactively, you learned to proactively structure tests that not only catch issues, but also prevent them from entering your codebase. JUnit's annotations, such as @test, and lifecycle methods like @before and @after, introduced new ways to organize and control test execution. These features gave your testing process greater flexibility and precision. By combining annotations with parameterized tests and test suites, you developed a strategy to execute multiple test cases efficiently. This approach reduced the complexity of managing large test sets. Integrating JUnit into your development process empowered you to verify that every part of your code functions as intended. This streamlined your workflow and boosted your confidence in the reliability of your software. In the final part of this module, you embraced test-driven development, TDD, a methodology that challenges traditional code-first, test-later approaches. In short, the TDD mindset encourages writing just enough code to pass a test, then refining that code through refactoring to keep it clean, minimal, and free from unnecessary complexity. The Red-Green-Refactor cycle became second nature as you wrote failing tests, developed code to make them pass, and then refactored to improve the structure. Recall that in the red phase, the test is expected to fail, while in the green phase, just enough code is written to pass the test. Finally, in the refactor phase, you improve the code structure. This cycle promotes continuous improvement, leading to a more maintainable and adaptable codebase. To complement this, you explored continuous integration, CI, where tools like Jenkins and Travis CI automate testing and integration. By regularly merging and testing code, CI catches bugs early and keeps your code in a deployable state, reinforcing TDD best practices. The skills you've gained in this module lay the foundation for writing clean, efficient, and well-tested code. With these capabilities, you're ready to create reliable software that meets the highest standards of quality, while keeping your development process efficient and effective. Congratulations again on completing this module, and happy testing. Imagine you're in a hiking challenge in the Great Smoky Mountains. Your team starts from different points with the goal of reaching the centre together. Using the Never Lost in Woods GPS electronic device, you and your team get live updates from other hikers and collaborate amongst yourselves. If someone strays off course, the app quickly shares the mistake and everyone is updated with the latest correction. There are no dead ends here. In software development, continuous integration, or CI, works the same way. Developers get immediate feedback on errors, and changes are instantly shared across the team. This video will explore CI in test-driven development and introduce two popular automation tools, Jenkins and Travis CI, highlighting their key benefits and challenges. In software, continuous integration is the process where developers frequently merge their code changes into a shared repository. By automatically testing each update, issues can be caught early and corrected, ensuring every small change is validated before the project moves forward. Here are the 3 main reasons CI is so critical to the success of development projects, especially if they're complex. First, CI tools automatically test your code frequently, ensuring that improvement is built into every step of the development process, which reduces errors. Second, like a well-worn trail, automated testing creates a consistent environment, delivering dependable results every time. And third, automation allows developers to focus on building software, not constant corrections, boosting productivity. If CI is so beneficial, why isn't everyone using it? The most pressing challenge is the initial setup cost, which requires significant time and resources to establish an automation environment. However, the long-term savings typically outweigh this investment. Just as hikers must promptly report wrong turns to the group, developers in automated TDD must be disciplined in addressing errors immediately when caught by tools like Jenkins. And, naturally, the never lost in woods device needs software updates to stay synced with the latest GPS technology. Similarly, automation tools must be maintained to keep up with evolving clients' requirements. In unfortunate situations, incorrect GPS tracking or flaws in software updates can cause the Never Lost in Woods tool to suggest you're on the right path when you're not. This situation is referred to as a false positive. In TDD, this can happen when a test passes but should fail due to a wrong check, flawed logic, or timing issues. Despite these challenges, the long-term benefits of CI make it an essential part of modern development. Thankfully, developers don't need to build CI tools from scratch. Jenkins, which is open source, and Travis CI are 2 widely used automation tools in the test development space. Simply put, Jenkins is like creating your own path, offering full customization and freedom, while Travis CI is like using a travel guide, ready-made and easy to follow. For hosting, Jenkins requires you to set up your own servers, giving your team full control, while Travis CI is a pre-configured hosted service. It's like choosing your own campsite versus following a guided tour with predefined stops. Jenkins also supports a wide range of tools like Git, SVN, Maven, Docker, and Kubernetes, whereas Travis CI primarily focuses on Git. Jenkins is more of a generalist, whereas Travis CI is specialized. How easy are these tools to implement and use? As you might expect, while Jenkins is flexible and supports multiple tools, it does require more setup, which costs. Travis CI, integrated with Git, is much easier to implement and use, needing only a .travis.yml file in the repository. Overall, the choice depends on your project's needs. Jenkins offers flexibility and control, while Travis CI is easier to set up and use. Both tools are powerful, but suited to different workflows. In this video, you learned how CI and test-driven development works like a team of hikers, navigating their way without getting lost. With the right tool, everyone's progress gets corrected and adjusted in real time, reducing errors, ensuring consistency, and ultimately boosting productivity.